morning. We are starting in 2 minutes, so please take a seat.
Okay, I think that we can start. Sorry. So welcome everybody to the second session of our Innovation and Networking Days on Battery Technologies and e-vehicles. First of all, I would like to thank all the people that joined us yesterday, in person or virtually. To give you some numbers, we had about 50 people here present and almost 200 people follow us in streaming. So I think that they are good numbers. And with the aim to surpass those numbers and reach a higher audience, today in the morning we have programmed high-level technology talks on the Electromobility Technology Workshop, Driving a Greener Value Chain by i-HeCoBatt project. Particularly, we will explore all the electric vehicle value chain from a life cycle perspective through 4 different blocks, including advanced materials for batteries, innovations in EV components, infrastructure challenges and success stories on large-scale demonstrators, and end-of-life possibilities to boost circular schemes. After the networking lunch, we will have a B2B and expert to seminar brainstorming on future technologies for batteries and EV vehicles in the EU funding context. Main conclusions arising from the discussion will be compiled in a white paper intended to highlight e-mobility technology hotspots where EU funding should dedicate more resources. For those of you joining today, please remember the housekeeping rules, so in the screen, not now, but I think in a moment. And questions and ideas for discussion are welcome through Slido, following the code that we will show in a moment. So I think that we can start with our first block on advanced materials for batteries. For that, let me welcome our speakers. Good morning, Professor Luis Miguel Varela. Good morning, Dr. Maria Martinez Ibáñez. Good morning, Dr. Warda Hidushi. Good morning. And good morning, Dr. Alex Friesen. So in this block, we touch every single component of the battery, anode, cathode, and electrolyte, from materials to manufacturing challenges. But first of all, we will have a general overview of battery materials state of the art and current and future trends, which will be offered by the Professor Luis Miguel Varela Cabo. Professor Luis Miguel Varela is coordinating the Nanomaterials Photonics and Soft Matter Group at University of Santiago de Compostela. He is also a member of the main European platforms on batteries like Battery Europe and Battery 2030, and he is the founder of the Permanent Seminar on Energy Transition and Industrial Competitiveness, Expertus. So with all these ingredients, I can wait to hear from you. So please, Professor, the floor is yours.
Thank you very much. Good morning, everybody. I don't know if I will be able to see my presentation.
I think so. I hope so.
Hopefully. Well, thank you for being here at 9 o'clock, the second day of the meeting, and not having rushed to the airport, as everybody probably is looking forward to do. Hopefully not after my presentation. Oh, sorry. It doesn't work.
Maybe it's on.
Told me it's on, yeah. We ran out of batteries, probably. Well, in the meanwhile, I will try to give some. Oh, it's already working. You did it. Okay, okay. So, as I have been asked by the organization, first of all, I thank the organizers for inviting me, and also for organizing this Expertus meeting in the afternoon that I hope it's of your interest, and we can provide you some non-technical facts, which is something that is sometimes forgotten in this kind of meetings. Everybody becomes very technical. Let's see. No. Nobody knows why.
No, I don't know. So you can manage from the.
Okay. Yeah.
Sorry.
Okay, so we will manage from there. So please go to the next slide. Well, this is just the content, so please to the next one, which introduces the high technology of batteries. This is high tech. Well, this was high tech indeed in 1912. So it's an electric vehicle. Indeed, the electric vehicle dates back to 1827, and it was introduced by a priest. Priests then were doing very good thermodynamics because they were also very active introducing very efficient engines, like some of the most efficient in thermodynamics were introduced by priests, so they were very active in thermodynamics. And the question we should ask is, why didn't it succeed? Why didn't all the transport, the mobility became electric in the first part of the 20th century, or even in the 19th century? Essentially because we had a very abundant and cheap fuel, which was petrol, yeah, and it still is petrol. Please go to the next slide. You cannot see it with me, but the expansion of electric vehicles is becoming exponential. I don't know exactly if because they are the final and ultimate technology we will adopt. In this meeting, we would like to think so, that it is the ultimate technology we will adopt as a society, but we are not sure at all. Because, well, let's see what happens in the future. No, it's not written. But it's actually expanding not only because of technological issues, but also because of legal and political reasons which are promoting the expansion of the market, which is, as you see, exponential, but you cannot see it very detailed, but it went from essentially zero in the beginning of the last decade to more than 10 million passenger light duty vehicles deployed worldwide now. So please go to the next slide. Well, an electric vehicle, it's made out of different pieces. Behind me, you have a supercab. Most of you, it's already working? Oh, okay, thank you very much. So most of you know all those pieces much better than me, so I will not become very technical because it's not what the organization asked me to do. But I would say that it demands, its deployment demands a huge industrial transformation, which is something which is going on currently, and we don't know exactly which rate it should go at, and we don't know exactly what are we going to do with some parts of the previous and still existing thermal industry, which will replace inverters, exhausting pipe with inverters, which brakes with some other things. So it's a huge technological challenge which is going on. It has a lot of technical issues, of course, but also some non-technical facts that must be considered, because I will talk a little bit later about that, but we need to replace petrol with metals, essentially. So what are we going to do? Now, we have had a lot of wars on petrol, and we are going to have wars on metals, or what? Because we don't have so many of them available, as you will see later. Well, which are the dominant technologies? Well, everybody probably knows this quite well, but the dominant technology still is lithium-ion. And according to most of the reports, it will be dominant for many years to come, or maybe definitely, no one knows. Of course, for cathodes, the dominant technologies are these lithium oxides, lithium metal oxides, or recently it has become very fashionable to come again to lithium iron phosphate or to nickel manganese cobalt, which is the next frontier we have to overtake. They are laminar materials, they are layered materials in which essentially insertion takes place. Not only, but mainly this is the main technology that is deployed. It's the mainstream in battery cathodes nowadays, as you well know. Oh, sorry, it's a little bit unpredictable. And here you have a very interesting review coming from the people in Battery 2030 Plus. It's Christina Edstrom, as far as I can remember, is there, and Petr Novak, and many other people. And here you have more or less the basic, the essential facts that must be considered when you face the problem of deciding what you should do in your next paper, in your next proposal. Of course, the two most important figures, that I will only talk about them because I don't have time enough, are gravimetric density and volumetric density. We are about 180 nowadays, 190 watt-hour per kilogram, and we should be, we are expected to, we are supposed to go above 250 at the end of this last decade, sorry, around 2030, 2040, we should be more or less there. According to, well, this at pack level, at cell level, we should be a little bit higher, of course. According to volumetric energy density, in watts-hour per liter, you have to, we are supposed to be above 600 or 1,000, depending on pack or cell level, in 2050, but we are now more or less half or two-thirds of those figures. So if you want to start a career in batteries, you should take these figures into account in order to know what you are expected to do, because this Battery 2030 Plus is more or less fixing the standards now in Europe. Yeah? Well, this is another battery-fueled vehicle, which combines the thermal engine with the electric engine, as you all know. It's a hybrid vehicle, and it means that we are not burying the thermal engine yet, which is something that we have to consider seriously. Are we burying the thermal engine or not? Or not yet, or never? Which is the appropriate answer? Nobody knows. But this combines both. You have different architectures now in the market. Well, here I show this. I think that it's the one I show there is the parallel one, but I'm not sure because I am in front of it, so I don't remember exactly. You have the series architecture, you have the parallel architecture. Both of them have different pros and cons, and well, more or less And the basic or the essential facts are summarized in that table coming from that paper. So if you have access to the presentation later, you can check them. It's not worth it to go into the details now. Of course, we have the hydrogen fuel vehicle, which is also an electric vehicle. This offers a lot of questions for the future, because probably we will discuss this in the afternoon. Nobody knows which will be the dominant technology in 2050. Will we have battery cars? Will we have hydrogen cars? Will we have a mix? Hydrogen for long distance mobility, batteries for urban mobility. How do we solve the security issues arising from that tank over there at 700 or 900 bars, which is something that I will not like to be seated on top of it, but it's like that. But on top of that, you have also some other issues, like, for example, a double conversion. You previously convert electricity into hydrogen, then hydrogen into electricity in the fuel cell, and then you move the engine. I have been teaching thermodynamics for more than 25 years now, although it is not my main dedication, because my main dedication is statistical mechanics, but thermodynamics tells you that in each single transformation you lose a lot of energy. So this offers serious questions about efficiency. So let's see what happens. Of course, sometimes it doesn't work and sometimes it's too fast. This is a funny pointer. Yeah. The basic component of the hydrogen fuel vehicle is the fuel cell. You have different technologies, comprising from normal naphtha-ion membranes, polymer membranes now, to solid oxide high temperature fuel cells, or to molten salt fuel cells. But the technology is well known. Of course, we are designing new materials for high temperature fuel cells or for alkaline, but the technology is quite well known. It is only the inverter of an electrolyzer. The problem is the efficiency, always, as in any other issue, but also the price. I mean, the price nowadays of the fuel cells is quite high. Of course, industry has accustomed us in the past to decrease the prices quite quickly once the technology is adopted, but it hasn't been adopted yet. So, and these are the main vehicles you have with a fuel cell now in the market. This is a polymer. Most of them are with polymer, or all of them are with polymer technologies. Some of them high energy, some others are. But these are the cars you can buy now. Other issue is where you are going to refuel your tank up to now, but you can already buy them in the market. Yeah? Well, I'm going back to moving into the advanced materials, which is the second part of the talk. Of course, we start with cathodes for batteries. I won't say anything else about fuel cells, at least not in this talk. And for cathodes, you have essentially these these four different type of materials. The olivine, which is just like there. This is the essential plot of potential versus specific capacity, and you see that the olivine doesn't perform that much well with specific capacity. But you have the main technology, which is layer oxide, as I told you previously. You have a plethora of different chemistries moving around. We were discussing yesterday at dinner that one of the main problems of the research in this kind of devices is that it's very much trial and error research. I mean, you take the periodic table and you play with another metal which nobody has played previously, and no one really knows how to choose the most efficient combination of metals, the most efficient alloy. But well, up to now we have come with all those you have there, comprising many metals, different metals, to get these layer oxides for intercalation. And of course you have the spinels, which perform quite well. They are high potential materials. They are high potentials, but they are not very specific capacity high. And then you have all those fluorines there that it's a lot of specific capacity, but they are not among the ones with the highest potentials. So Those are more or less the basic technologies we have nowadays. I would say that we are around generation 3A. I don't know exactly the gigafactories that are being deployed at the moment if they are moving into 3B, but I would say that the mainstream technologies or the mainstream generation deployed up to now and being deployed at the moment are 3A, and we are moving into 3B. Of course, you see that then silicon will gain in the future. It's expected, according to the strategic energy plan, the set plan of the roadmap to 2025, we should be deploying silicon and silicon carbon alloys very soon, and of course later we should move into more lithium sulfur and all solid state with lithium anodes, which is more or less the holy grail, and then the holy grail itself, which is lithium air, is generation 5. So this is more or less the expected trend according to the set plan. Yeah. As for anodes, well, we have these different technologies or different materials, alloys, carbon-based, transition metal oxides, and of course silicon, which is the one with the highest capacity. But for lithium, which, as I told you previously, that star over there is the holy grail, but no one is really sure how to produce the battery, or at least not yet. I would say that graphite anodes are the predominant technology in the market, but probably you have more information than me, and you correct me. Don't hesitate to correct me if you think I am wrong, because I am in a university and not in a factory. So you say, no, we're not, graphite is not the dominant and some other is. But I would say that graphite anodes are predominant up to now. Yeah. The figures of the capacities and so on of the different materials, you have them there coming from this review, so you can check them later. No, don't worry. It's we can joke about, so it's good. Yeah. And here again, you have to go to the set plan and to see which is the expected trend for the evolution of anode technologies, and also to the different reviews that Battery 2030 Plus have reported up to now. Moving very quickly in order not to consume more time than expected to electrolytes. In this I am totally sure because it's my modest specialty. I'm devoted to new generation electrolytes, ionogels specifically. But for sure, the dominant technology nowadays are liquid electrolytes, still using old-fashioned carbonates. I would say also some other solvents like DMSO, but mainly carbonates with additives also based in carbonates, and those different combinations of lithium salts. Lithium TFSI probably is the preferred one because of its stability, and it doesn't contain any kind of halogen like this fluorine, which is very easily producing fluoridic acid, which is absolutely inconvenient. It likes to pass two at a time, yeah. Not one. Of course, as Sophie told us yesterday, the ionogels are quickly being developed in the labs, and now they are supposed to go to the factory in very few time, in which you have a solid matrix, you have a polymer matrix coming from silicon with solid gel technologies, or using a spinodal decomposition of any other kind of polymers, and you produce a gel matrix in which you have it's a hybrid in which you have a liquid inside a gel matrix, and it's mechanically rigid, but it's also very highly conductive. So it combines both good properties. You see there a liquid, a gel that we prepared in our lab. It's like this in order to show you that you have no fluency. It's a rigid matrix, but also you have liquid characteristics. If you compare the infrared spectra in your side with the gel matrix with the liquid matrix, you see exactly the same. I mean, most of it is a liquid, so you have conductivity of liquid state. The conductivities are compared in the bottom right part of the slide, but the gel will be me, so you cannot compare directly now. So you will see that later, and you see that all thermal history disappears. You have a perfect thermal stability, and it's a very interesting material. Anyway, they are coming. They are not here yet. We are producing them in the labs, and I would say that France has a moderate, or not too moderate leadership in that. Yeah, they are producing. They have very good producers of ionogels in our neighbor country. It likes to pass too, as I told you. Yeah, and then comes the solid, the pure solid state. These are considered all solid. I mean, you can produce solid cells or with solid electrolytes, but they are not conventional solid. They are hybrid biphasic material. And here you have the solids. Of course, you have these sulfides, you have hydrides, nasicon, and you have polymers, which is the two basic problems that we have nowadays. Low conductivities, low ionic conductivities, which is the interesting one for sure, but also the contact at the interface. If you want to ensure good contacts at your interface, which is the essential part of the device between the electrolyte and the electrode, in the electrolyte-electrode interface, be it the anion or the cation, the CEI or the SEI, you have to pressurize at moderate to high pressures, around 70 bars or 60 to 70 bars is the conventional pressures being used now. Or you have to grow thin layers of your electrode on top of your electrolyte, on top of your electrode. Of course, this is very slow, and it's difficult to upscale to industrial scale. So, well, let's see how it evolves, but they have these difficulties. Moving very quickly to the last part of the advanced materials and close to the end of the presentation, I would say that sodium batteries is an issue that is they are here to stay for sure. They are now comparable with lithium, and we have the luck here in Spain to have a strong leadership, and for sure the person who personalizes this leadership is here in the audience, so you can talk to him later, which is Professor Teófilo Rojo, which previously was I took a paper of him, and also Maria Forsyth, because undoubtedly they are among the world leaders on this technology. So if you are interested in sodium ion, it's your opportunity now. Yeah? You have him here, yeah? And also people from TIC Energigune. Yeah? But also I compare the technologies of magnesium and aluminium there, and how do they perform in a paper of Stefano Passerini with some other people. Stefano Passerini is the vice president of Battery 2030 Plus. But of course, you cannot see the aluminium and magnesium part, because once again, I am on top of it. Yeah? That's like that, yeah. Problems of the online. Here. Well, going very quickly to the last 3 slides of my presentation, my question here is, which are the challenges to global electrification of transport? And I here go again to non-technical issues, because they are very important to consider. This is not only a technical problem. I would say it is not even mainly a technical problem. It is a political and a social problem, and we are seeing that very, very clearly in these difficult days. Here you have the different evolutions and roadmap of different powers, starting with China, also the United States and Japan. And for sure you have the European state, where Europe is now, and I would say it is not competing with these major actors, major players of the business of batteries. Yeah, there you can see how they expect to deploy the different technologies in the years to come, and well, we must rush a lot to keep up with them. So this is something that we have to consider. We have been leaders in thermal technologies for more than 150 years now, and now we are abandoning that, which I don't say it is not convenient, yeah, but we have to be realistic. We have to know where we are, yeah, and we are competing with these major actors, which are really more advanced than we are. Yeah. I don't know exactly. It's here that I have to. Well, here you see which are, we have a problem of materials, and here you see which are the major producers of batteries. For sure, you see the size of the circle of China. Yeah? In gigawatts, they produce more than 550 gigawatts hour now. Compare that to Japan or to the 44 of the United States, or less than 60 of all the combined European efforts nowadays. And there, on the left side, you have the critical raw materials for lithium-ion batteries, considered by the critical raw materials according to the European Union. And we have a problem, because you see that of them, only Finland, and with, for example, the cobalt, and some parts of Norway with graphite, only on that we have a tiny fraction of the global production. So this is something that we have to consider. We are late in the race for batteries, and we don't have the appropriate materials, and most of them are in parts of the world which are geopolitically unstable and, of course, hostile, some of them, to us. Yeah? And we can say that clearly nowadays, because the war has already erupted, unfortunately for everybody. And so this is the mega factory pipeline. There are more or less 200 battery factories in the pipeline, but 148 of them are expected to be produced in China. So only 21 in Europe, and 11 in North America, 20 in other parts of the world. So this also must be considered. We must be very wise choosing the technology, and we must be absolutely realistic in the position we are, in order to decide which materials are we going to use, which route do we want to follow to the electrification, which rate should be adopted. And finally, I would say that this material challenge also requires, this is a very interesting paper in Nature, just reported 1 year ago, or less than 1 year ago. According to them, without recycling a massive part of the metals, it's not possible to do this. We need so much lithium that it's absolutely impossible to produce it primarily in mines, to transform large fractions of the cars that we are using nowadays in our highly organized societies. So, thanks a lot for your attention and for not sleeping while I'm talking, which is probably what you should be doing at this time. Thank you very much. Questions now or later?
Sorry for the issue. No. It's very interesting. So thank you very much, Professor, for this exhaustive overview of the... You have reached all the value chain already, so thank you very much. Now it's time to go to more technical details on the batteries, and it's time for the Dr. Maria Martinez Ibañez, expert in the field of applied chemistry and polymeric materials, and leader of the polymer-rich electrolytes research line at SiC Energy Gune. Dr. Martinez is the coordinator of the Safely Move Horizon 2020 project, and is going to present the great advancements that they have achieved. So thank you very much.
Thank you.
Good luck with the...
with the pointer. Okay. Thank you for the introduction, and good morning, everyone. So I would like to thank again to the organizers for inviting me and for providing the opportunity to present the results of this project. And today, as I was mentioning, I will talk about Safely Move project, a European project, and Safely Move stands for Advanced All Solid State Safe Lithium Metal Technology Towards Vehicle Electrification. This project was granted 2 years ago in the call H2020 LC-BAT-01. The duration of this project will be 48 months, sorry. So this means that we have reached already the midterm of this project. We are 16 partners, and we are covering the whole value chain. So we have partners in charge of material manufacturing. There are universities, research centers, battery manufacturers, and also we have some OEMs, so end users. And of course, we have partners that are supporting CIC Energy Gune on the administration and coordination, and also in charge of the assessment of the LCA and the recyclability of Safely Move technology. see that it's a challenge to work with this pointer. Oops. Okay, here. So talking about challenges, so here I'm summarizing the challenges that move us to design this project, the Safely Move concept. So as we all know, the electric vehicles battery market is dominated mainly by lithium-ion technology, as Luis Miguel just presented. So here we know that this technology is already reaching the theoretical limits. So for this reason, we need to move for new technologies. And on this regard, lithium metal is as the holy grail, as has been mentioned before, but the need of changing to this type of anode also make us to consider to replace the highly flammable liquid electrolyte that are used currently in lithium-ion technology. So in this case, there is the need to introduce the concept of solid electrolyte. In this case, in Safely Move project, we will move towards hybrid electrolytes containing both ceramic and polymeric phases within this electrolyte. And currently, we can see that there is this technology, solid-state technology, based on polymer electrolyte and lithium metal is already in the market, thanks to Blue Solutions, where we have the Blue Car and Blue Bus. But there are some limitations on this technology currently that are mainly related to the low energy density ascribed to the use of lithium iron phosphate as a positive electrode, and also the operating temperature that needs to be about 70 degrees. So this requires a heating system to maintain this temperature, and then there is a reduction on the efficiency. So considering having this all into account, the objective of Safely Move project, right, okay. So the objective of Safely Move project is the design of solid-state batteries, for high energy density, both gravimetric and volumetric. And to achieve this goal, we have 4 main points for action. The first one will be the design of high specific capacity lithium metal anodes. Then if we go to the cathode, we are looking for nickel-rich layer oxides. This will allow us to reach higher energy densities thanks to the intrinsic high voltage of this material. And then to combine all this together, we need to have a solid electrolyte that will need to provide high ionic conductivity in order to reduce the operational temperature of the battery, but also provide enough stability with both positive electrodes, so stability to high voltages, and also compatibility with the lithium metal. And the fourth point of this project is to try to bring all these materials together. So for this, there is a great effort and a lot of work on the study and the tuning of the interfaces among the different materials. So when we conceive the Safely Move concept, or not? We are trying to get another, so if you want, I can ask him. Okay, okay, we'll be here. Thank you. Okay, perfect. Okay, so as I was mentioning before, when we started the project, we realized about something that everyone knows, but the requirements for a material that needs to be in contact with a cathode or with a lithium metal are different. So for that reason, we decided to design for this type of electrolyte a V-layer electrolyte. So when we are talking about the electrolyte, we need to have, of course, good mechanical properties to work as a separator, high ionic conductivity, but also we need to consider the interface with the lithium metal. And then if we move to the other side of the battery, if we think about the cathode, we need to have, in this case, high stability, high anodic stability to afford the voltage operation of the cathode. So having this in mind, we decided to design 2 different hybrid electrolytes. So we have 2 different hybrid ceramic polymer electrolytes. This means different chemistries for the polymer, but also different chemistries for the ceramic part. If we move to the next slide. Okay, thank you. So then if I go to the way in which we designed the project, we have 4 different phases. So there is 3 steps, development of material level, but this is also translated into 3 different generations of batteries, of cells. So we already reached the development of the level 1 materials. These have been tested in small cells, so coin cells and monolayers. The feedback obtained for the design and testing of these materials has been used for the synthesis and development of the 2nd generation that now has been already shared with the rest of the partners in order to produce the 1st generation of 1 ampere-hour cells. Then the testing of this will go to the material producers in order to allow them to improve the chemistries of this last generation of safely moved materials, where we will move to 1 ampere hours and we will scale up up to 10 ampere hour cells. And in the last phase of the project, we will have the design of the battery module of 24 volts and 10 ampere hour. So if we go to the next slide. Great, thank you. So now that we have more or less in mind which are the objectives, how is the way in which we are working, I will summarize briefly the main results that we have obtained and the main milestones that we have reached until now. So as I was mentioning, the first milestone is related to this level 1 materials development. So this was done at the very beginning of the project, so in the month 7, and it was based on the development of the different components of the battery in order to produce the first generation of cells. So in this case, we have the core chemistry of the materials is the level 1 NMC, that is NMC 811. Then we have the lithium metal foil, something that I didn't mention here, but is also an advantage, is that in this case, the lithium metal is a lithium metal foil. There is no copper current collector, so this will have also an impact on the price of the battery. But of course, we'll have also many challenges if we consider the manufacturing. So I didn't mention at the beginning of the presentation, but also that will also imply a great innovation within this project is the manufacturing of solid-state batteries, because currently the market is dominated by lithium-ion technology. So now we need to reconsider how to change this and translate to move forward for the solid-state battery manufacturing. So there is a work package within this project that is fully devoted to this design. And then the third material that was developed within this first milestone, as I was mentioning before, is the hybrid ceramic polymer electrolyte. So in this case, it happens the same. So the ionic conductivity is behind me. So in this first generation, we were targeting the ionic conductivity of 10 to minus 4 Siemens per centimeter in the range between 40 and room temperature. So we were close to this target. And of course, this is something that now has evolved and has improved if we consider the level 2 material generation. If we go to the next slide, please. Okay. So the second milestone of the project was reached at the end of the first year. That was, as I was mentioning before, the manufacturing of the first generation of monolayer cells containing all the safely moved materials. So in this case, the main scope or the main goal of these cells was to assess the compatibility. So as I was mentioning before, within safely moved, we have many different interfaces. So we have the interfaces that we may have in any battery, so between the cathode, the electrolyte, and the anode. But if we consider the different materials, we have also a lot of intra-interfaces. So just in each of the hybrid electrolyte, we have also the interfaces between the ceramic and the polymeric phases. So there is a great effort devoted to the analysis of these interfaces in order to understand what is going on between all different interfaces, and also to tune the properties on the materials in order to enhance the performance of the battery. So if we go to the next slide, okay. So the third milestone that we have reached within the project, as I was mentioning before, is the development of the level 2 materials. So thanks to the analysis of the post-cycling of these safely moved Gen 0 cells, we have been able to identify which are the main failure mechanisms, where we may find some incompatibilities between the different materials, and this has allowed us to develop the second generation NMC, where here the core chemistry has been kept constant, so we are working with the NMC 811, but what we have changed is the chemistry of the particles. So there is a coating strategy in order to improve the compatibility with the catholyte or the hybrid electrolyte. Then if we go to the lithium metal, also we have decreased the thickness of the foil. This is not focused on the performance, it's mainly focused on the energy density that we need to reach at the end of the project. So this will have a great impact. But we are also exploring the overcoating techniques in order to improve, in this case, the interface between the lithium metal and the hybrid electrolyte by means of compatibility to decrease the interfacial resistance and improve the cycle life of the battery. And then now if we move to the third pillar of this project, that is the hybrid electrolyte. So after assessing the level 1 materials, we have identified the main points that we need to improve on this part, that is, as I was mentioning before. One is the ionic conductivity, but also is the compatibility among the ceramic and the polymer phases. So here we have played with the chemistry of the polymer by itself, but also we are tuning the properties of the ceramic particles by playing with the particle size, but also with the functionalities on the surface of these particles in order to improve the compatibility among both phases. So these materials have been already developed, these level 2 materials, and have been provided to the partner, in this case is the tech in charge of the manufacturing of the first generation of 1 ampere-hour cells, and this milestone will be reached just before summer. So if we go to the next slide. Okay, so this was mainly the summary of the results that we have currently obtained within this project. And now I will move to the more general expected impact that we hope to have at the end of the project. So I have divided in 4 main points. The first one, of course, is the increased energy density. So we know that we have a target at really high value for both gravimetric and volumetric energy density. And we hope that if this is reached, we will have a great impact, mainly because we are replacing lithium metal will allow us to reach this target, but also the coupling of this lithium metal with a high voltage active materials, as is the case of the NMC, replacing what we have currently in the state of the art, or mainly what we can find for solid state, that is lithium iron phosphate. Also, this high energy density will have an impact on something that is really important for the people that will be using this type of EV electric vehicles, that is the range of driving autonomy. So if this energy density is translated into the kilometers that this vehicle will be able to drive, we are talking about 700 kilometers. So for a cycle life of 500 cycles, that we have target for the end of the project, that is the 2024, this will be translated in some hundred thousands of kilometers. If we go to the next slide, the other 3 impacts, one of course is safety. There is a great concern of the use of flammable or volatile organic electrolyte, organic solvents. So we assume that the replacement of this electrolyte with a hybrid solid electrolyte will allow us to have a higher safety of the battery. So this electrolyte that we are currently designing, they are stable at 300 degrees. So this will allow us to also, so this will have a 3-fold impact actually, the safety. So from one side, we improve the safety of the battery, of course. We also improve the battery lifetime, but also if we consider the design of the battery pack, this will also allow us to decrease the cost of the battery and the design. So this is related to the 4th impact that I was mentioning, that is the cost of the battery and the pack. And then the last one is the European battery value chains, where in Safely Move we are bringing together all the necessary actors or experts in the different components. As I was mentioning, we are covering the whole value chain, so there are material producers, cell producers, end users, and of course other research and universities. So we hope to reach the targets that we have defined for the project, or at least stay as close as possible to these values. And if we move to the next slide. Okay, so here I just wanted to share with you the website of the project. Of course, you can follow us in the newsletter, Twitter, and if you want to know more about this, don't hesitate to contact me or come later and talk to me. And thank you, everyone.
Thank you very much, Maria. We will have some questions. I think that we will have time to some questions after all the presentation. So you can also make the questions through Slido for those of you that are connected in YouTube. Okay, so now it's time for our next talk. We are going into details on the anode materials. For that, let me introduce you to Dr. Warda Hidushi. Good morning. Dr. Hidushi is R&D battery engineer at Nanomakers, a French company dedicated to design, develop, and commercialize patent silicon-based nanoparticles for different applications. So, Dr. Hidushi, the floor is yours.
So I'm glad to be here today with you to talk about the promise of silicon in the battery. Next slide, please. Current batteries are, mainly composed with a graphite anode and NMC cathode, and to boost the development of electric vehicles, you need more autonomy at low cost. So for this, there is a very strong demand for innovation with research aiming at improving density and lifetime. On one hand, there is technical improvement on the cathode material, and on other hand, there is also industry research effort cast on improving anode capacity by using silicon instead of graphite. Next slide, please. Effectively, silicon is a very promising material for anode because first, he has a very high specific capacity with 3,500 milliampere per gram. Also, he has a very high voltage at 0.5 volt compared to the lithium electrode. However, his integration to batteries currently is limited first by its large volume expansion during cycling, which can reach about 300%. So it leads to a material decohesion and to a loss of electronic and mechanical integrity. The second issue is the control formation of solid electrolyte interface, which leads to a gradual electrolyte and lithium consumption. So we have a very enhanced no passivating behavior. Next slide, please. Currently, on the market, there is some battery manufacturer like Samsung or LG which integrate silicon on their commercial sales. But due to the capacity losses of the pure silicon, there is only oxide silicon with a limited quantity between 1 and 5%. For example, LG came with adding 3% of oxide silicon in their graphite anode, there can reach an. Thank you. Okay, thank you. So LG Chem can reach an energy density of 260 watt per gram. The conclusion here in this slide is to allow the commercialization of this next generation of lithium-ion batteries. You need solve the cracking and the SEA instability of the silicon. One solution for this is to work on a silicon-carbon composite. Here is a modelization on the influence of silicon content in the anode, on the specific energy and on the energy density. It's not a surprise when you increase the silicon content in the anode, we increase also the specific energy and the energy density. But here we have a value which is remarkable, is the 30%, because when we had a quantity of silicon over 30%, we can see that the effect on the specific energy or energy density is less and less visible. Here is the influence on the mass and the thickness of the battery. In this modelization, you don't take in account the casing of the battery, but only the composition inside the battery. When you are adding, when the quantity of solution is increased, effectively the mass and the thickness of the battery decrease. So it's very good for the next generation of batteries. And here also you can see when the quantity is more than 30%, the effect on these two values, mass and thickness, is less and less visible. So Nanomakers, which is a company which produces silicon, is exploring the silicon for the battery. For these nanomakers produce silicon nanoparticle by an industrial process, which is laser pyrolysis. This process use reagent gases. Here is a silane and acetylene. First, the silane, which is the source of silicon, is injected and cross a dioxide carbon laser, which break the bonds between silicon and hydrogen, and we have a nucleation and a growth of silicon particles. This growth is stopped very rapidly as soon as the particles leave the reaction, the environment. And after this, we inject a second reagent gas. Here is acetylene, which is a source of carbon. This gas is added is used to form a carbon layer around the nanoparticle silicons. In fact, when the acetylene is in contact of the particles with the hot, it will decompose and it will form this layer of carbon. So this process permits to obtain a very good size distribution of crystalline silicon nanoparticles with a very low oxygen content. We have also a very homogeneous, highly pure, and reproducible process. Alors, the carbon shell here is added to because it has many advantages. First, his role is to protect the particles of silicon from the electrolyte, and it favors the stability of the ACA and improve the stability the affinity with graphite and many other binders. Nanomakers work also in a silicon carbon composite synthesis. Here is R&D process, is not industrial process. For this, it use a petroleum pitch as carbon source, which is dissolved in a solvent, and we can add silicon nanoparticles produced by laser pyrolysis. And in this step, we can also add or not graphite. After mixing the mixed, and after evaporation, we introduce the material in the oven, and we heat at temperature under 1000 degrees. After then, we obtain a matrix of coke, which is the carbon, inside with nanoparticle silicon and graphite. After grinding and sieving, we obtain finally the silicon composite which is used in lithium battery. Some TAM images were done in this material, and we can see we have a very good distribution of the silicon on the carbon matrix. And we have also a good reproducibility at this stage of the process. Here we present the influence of silicon carbon composite grade on the electrochemistry performances. Here we have 4 composites, which one, all of them contain 7% of silicon and 93% of coke. The difference of them, it's the grade of silicon which is used. We have silicon nanoparticles which are obtained by pyrolysis, silicon nanoparticles by plasma, microsilicon, and oxide silicon. And we can see, thanks to their small size, here 40 nanometers, and his high purity, the silicon nanoparticles we can have a very good capacity with a very good retention capacity. In fact, here the carbon coating during the pyrolysis and the particle size reduce to the cracking and SEA formation. Here you studied also the presence of the graphite in silicon anode. We compare here two composites. One contain graphite and the other don't contain graphite. Both of them contain the same quantity of silicon, 12%, and we can see that the presence of the graphite permit to have a better capacity and a better stability of the material. The other way to add graphite in the anode is to add the graphite directly in the slurry. Here we studied a material with 5% of silicon and 95% of graphite. We can see also, even if the capacity is lower than the composite here, because the quantity of silicon is lower also, but we have a very good stability. For the composite, the carbon matrix, which is the coke here, protect the silicon from direct contact with electrolyte, and it permits also to accommodate volume expansion. The conclusion is in his slide. We have 2K factors which will permit to increase the silicon content in the anode. First, we need to work on the composition of the carbon matrix, because the pitch has a very important effect on the silicon coating. And the second one is to develop an electrolyte more adapted for this chemistry of silicon. For this, Nanomakers is involved in i-HeCoBatt European project, which was presented here by Sophie Mayer. In this project, the silicon produced by pyrolysis is used as main anode material, combined with the solid electrolyte and NMC cathode. This project has many interests. First, to stabilize the ACA, which limit the consumption of lithium, to control silicon volume expansion, provide safety, and finally, multiply the specific capacity. Thank you for your attention.
Thank you very much, Dr. Guarda. It sounds really promising. So now it's my pleasure to invite Dr. Alex Friesen, which will focus on one of the biggest challenges in solid-state batteries, the electrolyte. So Dr. Alex Friesen is R&D leader on battery materials at Daikin Chemicals Division. He has been working in R&D for battery materials and process since 2011. So he has a vast expertise in lithium-ion batteries. So Alex is also one of the most active partners in our i-HeCoBatt project. And please, Alex, the floor is yours.
Thank you very much. Good morning, everybody. Today we'll talk about raw materials and manufacturing strategies for solid electrolyte batteries, also showing some results from our i-HeCoBatt project. But please let me introduce our company first, to introduce who we are and what we are doing. Daikin Industries is a global company with a headquarters in Japan. Mostly it's known from AC systems. But what many people does not know, that Daikin Industries has a quite large division for chemistry, a chemical division. Globally, we have, I think, around about 4,000 people working in the chemical department, producing a lot of specialty materials, coming historically from fluorine chemistry, but now we have also a transition to non-F chemicals. And our portfolio is quite broad, from polymers to gases to small, fine chemicals. Daikin Chemical global sites, we are on all continents. Of course, our headquarters are in Asia, but in Europe we have also quite strong capabilities. We have 3 production sites in Europe, in Frankfurt, in Italy, and in France. And our European headquarters are located in Germany. And our R&D capabilities also. This coming now to introduce our new R&D capabilities in Europe, especially our newly opened innovation center located in Dortmund in Germany. It was opened up at the end of last year, so maybe half a year. We are inside this building and working actively in several technologies. Our energy storage department for developing battery materials is also located here. And basically our strategy for energy development is that we, starting from synthesis, going through processing, formulation studies, preparing cells, preparing cathodes, and also electrochemical evaluation with analytical capabilities, also to have also postmortem possibilities. So basically the full value chain, but of course on lab scale. The Daikin Chemical Europe Innovation Center has 3 pillars. One is the foresight, which is more targeting really long-term trends, to understand long-term trends and industry. And our programs for R&D, and here we are divided in 3 programs. Energy storage, electric, automotive and 5G, and surface modification technologies. And we are located, and my colleagues who are also here, in energy storage materials. And the last pillar is the product push, where we trying to bring this technology to the market. So basically on a higher TRL level, where this technology can be brought to customers for specification. Daikin Chemical is already quite long in the battery supply chain, especially in the Asian market. So we do have a quite good portfolio already on the market. What we are producing is gasket materials for long-term application in cylindrical cells or prismatic cells. One of our bigger products is a cathode binder. And here we have several technologies, basically targeting nickel-rich NMC material with polymers, which reduces the processing issues with NMC, so gelation issues, etc. But we are working also on quite strongly on new binder systems, also new binder systems going away from NMP, such as alternative solvents or even dry process. One of our broad departments, we have also an electrolyte additives and solvents, so different kind of film forming additives or various kind of additives which are targeting specifically to increase specific properties of liquid electrolyte systems. And one of our newer products is a cathode binder with single wall carbon nanotubes, which directly incorporated to increase the conductivity of this products and also to increase the adhesion of the cathode. Globally, we are working also on all-solid-state batteries. Our three main targets or teams we are working on is binder. Here we are targeting with the binder system oxidic or sulfidic systems. Here we have also developed technologies for wet process and dry process. Furthermore, we have a quite good portfolio in coating technology, for example, which can be applied on sulfide-based solid-state electrolytes to make them easier to process or safer to process. And what we are doing quite active in Europe, not only, but one of our larger topics is polymer electrolyte systems or polymer hybrid systems, also the i-HeCoBatt project. So coming to the solid-state electrolyte systems, as you know, as everybody knows, there are several competing technologies, and each technology and each material group has their own advantages and disadvantages. So looking at oxides, sulfides, and polymers, oxides show the best-in-class stability, but the mass production feasibility is quite difficult because it's ceramics. Ionic conductivity is also good, but not the best. For sulfides, we have the best ionic conductivity by far, but definitely issues with stability and also issues with the mass production feasibility just due to the safety issues. In polymers, we have just the other vice versa. So the mass production feasibility is very easy, so it's an easy adaptable system. You can bring it quite easy to market. But anyway, we have stability issues, so it's not fully stable at higher voltages, for example, and ionic conductivity. So polymers itself are non-conductive for lithium ions, looking like in the traditional polymer electrolytes. And one other group is basically hybrids. In hybrids, this is also what we are doing in the i-HeCoBatt project. It's a very complex system, so we learned a lot in the last 2.5 years in i-HeCoBatt. I think they have a good chance to bring to combine the positive aspects of the different systems, but it's very difficult to understand this systems, and there is a lot of R&D necessary to understand and to bring this kind of system directly to the market. Coming back to the raw materials, I think you already showed the critical materials for cathodes and anodes, but looking only at the solid electrolyte raw materials, and the most promising one, there is, if we have to look on the critical raw materials as defined by the European Union, so the materials which we don't have in Europe, basically, many of these materials are included in our electrolytes, or in the solid-state electrolytes and the most promising electrolytes. For example, heavy rare earth materials, elements such as lanthanum, which is, for example, one main component for LLZO, or even for fluorspan is inside, so the basic component to produce lithium salts which contain fluorine. Tantalum, phosphorus, niobium, germanium. So anyway, and if you look at each class of the materials for solid-state electrolytes, you will find critical raw materials which we don't have in Europe. So this needs to be imported. So it's always good to have this kind of things in mind. To be also future independent and to be able to produce it also on a large scale. In combination of the raw materials, looking at the electrolyte costs, here's an example from one recent publication on the production costs of different systems, comparing oxides, sulfides, halides, and polymers. As mentioned, polymers are the most easiest to adopt, so the production costs are also the lowest one. What is interesting here to see is that sulfides, halides, and polymers are kind of close connected to each other. This is basically coming from the easier processing, so halides and sulfides are very ductile materials, so they can be processed quite easily in conventional processes, can be densified quite easily because the material is kind of flowing under pressure, which is not the case for oxides. So oxides in case of production costs are very, very critical, and here are some example from literature. What you can see on the right side is a graph comparing costs and membrane thickness of basically ceramics. And if you are targeting really full single ceramic membranes, so let's say what makes sense, maybe around about 20 micrometers, the membrane costs are very high because it's a very complex process. So there are several processes, but none of them is really easy to adopt. So it's very, very difficult to process a good quality and large amount and very bright layers. But anyway, there are companies who are trying it. I think the most promising example is QuantumScape, which they claim that they can produce. And I believe them they can produce, but I'm not sure at what cost. So looking at hybrids, just let me start with a short motivation. Here you see is two cells comparing. One cell is running quite okay. So on the left side, we have the example one. So this is NMC 811 lithium metal cell with solid polymer electrolyte, which contains of polymer, salt, and plasticizer. So it works quite well, so no issues. But on the other side, you have this same cell with a little bit different parameters or very thin layer in between. And what we see a lot in laboratory type cells. So at some point, there's a kind of short circuit. This means we have lithium dendrites, for example, in these cells, penetrating through the electrolyte and shorting the cell. This means polymer electrolyte systems are very good to process, but the ionic conductivity is bad. So we need to introduce plasticizers to increase the ionic conductivity. These plasticizers have the bad side effect that we have lower mechanical stability of these polymers. So there's no good system with this kind of, or no optimal system. So you have always some advantages. So in case this ionic conductivity and disadvantages than mechanical stability, for example. So what we learned or what we understand is this brings us to the point that we need a mechanical enhancement of this polymer electrolytes to provide a better or to produce a safe cell. So that's why we are introducing in our ASRA project composite material into the polymer matrix. First of all, to increase the ionic conductivity as well, and also to increase the mechanical stability. From ionic conductivity, I think this is also quite interesting aspect that there are two advantageous processes inside the polymer electrolyte, which is increasing the conductivity. First of all, we are reducing our crystalline phases inside the polymer, which increases the conductivity of the polymer itself. And by choosing the correct composite material, which is also lithium-ion conducting, such as LZO, we can increase also the conductivity through the LZO particles itself. So looking at the processing of this kind of membranes, here we are showing two comparable results, two comparable hybrid electrolytes, which with a low content of LZO inside. On the left side, you see an example of a polymer electrolyte with conventional mixing methods. In this methods, we don't have enough energy input inside the polymer electrolyte to really deagglomerate LZO particles. On the other hand, we have also sedimentation because we are using solvent-based processing. So while removing the solvent, LZO is showing sedimentation. On the right side, you see an example of our updated or developed process with including high energy input mixing methods, how to process really thin films and with a homogeneous LZO distribution inside a film. Interestingly, the films on the left side show better ionic conductivity than the films on the right side. Maybe this is kind of a surface resistance issues because on the left side the films are quite thick and on the right side the films are very thin, so something around about between 30 and 50 micrometers, something in between. Anyway, but this gives us the result or gives us this understanding that to have an advantageous ionic conductivity increase through putting LZO inside, we need to put more in LZO inside to generate some kind of LZO network where lithium ions can diffuse throughout the network with the advantages of LZO with, for example, a high lithium transference number to bring better electrochemical properties. So basically, this is what we are doing in Astrabanth. So this is some of our recent results. So we're trying to test how we can process very, very thin films and where is the limit in putting LZO and still have a good self-sustaining membrane which can be produced on a large scale. The films before, they showed 5%, and here you see a comparison from 10 to 50%. So for 50%, it was possible to process the film, but it was not possible to extract them from the tray without damaging them. So we see currently that something around 20 or 30%, there might be the sweet point with this easy solvent-based process. Currently, we are working on it. We are testing it electrochemically, ionic conductivity, and also cell cycling. And this is our, maybe next time we can show you here more results. So with this, I would like to conclude already my talk. So there are many competing solid-state electrolyte technologies. I think each technology has advantages and disadvantages. And it's difficult to predict which technology may be in favor. And so far, I think there is still no clear winner. I think many companies are targeting also different technologies. There's a lot of invest going on also in startups. And we don't see any trend. But what we see is definitely a promising trend for hybrid technology, which can combine the positive aspects of two different technologies and maybe with reducing the disadvantages of these ones. But it's still early to say how this hybrid technology might impact the full solid-state batteries with only one technology. Looking at raw materials from a use standpoint, I think many of these technologies have critical raw materials. This might be an issue at, so for R&D, I think this is no issues, but if we're looking at mass production in Europe, I think this might be a challenge. So we need also to think probably on alternatives. From the processing side, I think there is a very clear trends for polymer-based systems because they're just easy to process. So this is really easy system that can be applied, and maybe with this kind of approaches as shown here or shown what we are working with the partners in Astra project, maybe this is a possible strategy how we can bring it to the market also with room temperature conductivity. And looking at the overall cost of solid electrolytes, we believe that they will be, in the beginning, very high, but we see definitely a prospect to reduce these costs over time, and especially over a long run of upscaling after 25. Let me also acknowledge or thank the EU for funding inside the i-HeCoBatt project, and here we would also like to thank the i-HeCoBatt project and the i-HeCoBatt partners for the good collaboration and the good R&D talks. What was really good for us that we are still, so because we have this kind of very complex systems, I would like to thank that all partners are open also to changes. So we adapted our system also a little bit, and I think we are doing really good progress. So thank you all the partners, and especially also for this study, we would like to thank Fraunhofer IKTS, who provided the LZO powders for this study, and my two colleagues, Timo and Alexander, who is also here today for the work in the laboratory. Yeah, if you want to reach out with more questions or comments, please just feel free to contact me directly. Thank you very much.
Thank you very much, Alex. Okay, we are a bit out of time, so we have several questions on Slido, but what we are going to do is to forward these questions to the speakers, and then we will provide their answer. So there is time only for one question if we have from the audience, or if not, I have one question. For all of you, that is a general one in this regarding the intended European materials acceleration platform. As you have said, that battery R&D is based on trials and errors. So what is your opinion of this materials acceleration platform to boost or to speed up the research on batteries? I would like to, do you envisage some limitation? Do you think that it's necessary? I would like to have your opinion. You can use the table of it. All the panelists can answer. But if you want to start, please.
No, now it's. Well, I think it is completely necessary. I was there in the meetings when they were discussing the implementation of it, and as far as I understood, and it is contained in the reports of Battery 2030 Plus, it has two different aspects. One is a purely, let's say, artificial intelligence-based mapping of the current state of affairs in the field. So they will review more or less, or we as a body in Europe, we will review more or less all the materials and the chemistries we currently have. And then there's a second aspect in which, probably in the afternoon we will talk about Cluster 5 proposals. And if you take a look at these Cluster 5 proposals, we have something like high throughput computation to map new possibilities of materials. Of course, if we don't look for a smarter way of going into the physics details, not only the chemistry, but the physics of it, with its universality, to design new materials for batteries, then for sure what we must be doing in the meanwhile is to have a good high throughput system, not only computational, not only simulations, but also experimental high throughput, to become as efficient as possible discovering the new chemistries. Otherwise, we will lack much more than we already have done relative to other parts of the world, which are much more advanced than we are. So I am positive with it, optimistic to some extent with the results, and let's see what future brings. Yeah.
Okay, thank you. And those of you that are more close to the laboratories, do you think that it will be useful, or what's your opinion?
Yes, I think that is useful, and it's something that I don't know if I should remove this maybe. Okay. It's useful, and I think that it's mandatory to speed up the validation of the different materials. So HTT can be an option to speed up, also modeling or integrate everything together. But that's true that sometimes it takes too long from the design of a material until the final validation. So somehow we need to merge and reduce the timing to validate all the new chemistries that are required.
Okay, thank you. So, do you want to say something else?
Definitely, I agree as well. I think battery R&D is very complex, and I think
Thank you.
I think also I have very optimistic for the future because there is many laboratory and company which work on the development of the future battery and and about a very high capacity material.
Okay, so thank you very much. So we have come now to the end of the first block. Thank you very much to all our speakers for the valuable information provided. Yeah, thank you. And now it's time to delve into the innovative EV components. So I leave the floor to Evelina that will introduce you.
Thank you very much, Isaac, and thank you to all our panelists. So since we are a little bit of time of our agenda, I will quickly introduce our next panelist for our next block about EV components and lifespan boosting. So I welcome our panelists and I invite you to join the table. So we have Dr. Mikel Oyarbide from Citec Energy Storage, Senior Researcher in Battery System, who is joining us online. Mikel, can you hear us?
Yes.
Perfect, and you have the presentation ready. Excellent. We have also Dr. Luis Trilla Romero from i-HeCoBatt, representing Marble Project, and Dr. Egoitz Martinez La Serna from Ikerlan, coordinator of Liberty Project. So without stealing too much time, I will directly leave the floor to Mikel. Thank you, Mikel. The floor is yours.
Thank you very much, Evelina. So good morning to everybody. In this presentation, I'm going to show you, let's say, our vision about the flexible and advanced battery management system that we see in Citec. So this is the agenda that I prepared for this presentation. I'm going to start with the introduction, then I will go to define the main BMS objectives, then I will go through detailing, let's say, the basic BMS protection and the basic SOX estimation algorithms, and finally I will conclude the presentation with advanced SOX estimation algorithms that we foresee for the next future. So first of all, a little bit about me. I studied Industrial and Automatic Engineering back in 2009 in the University of Mondragon. Then I joined to Citec and I started working for my PhD, where the title of this PhD was the development and implementation of state of charge and state of health estimation for lithium-based energy storage system. Then I did a research stage in Fraunhofer ISE back in 2015. And my knowledge and expertise is about lithium-ion inner state monitoring. I'm very focused also in the BMS specification, design, and validation. And I'm very used also to work with large battery pack management system. So I would like also to present my institute. So Citec is an R&D center located in San Sebastian in Donosti, and we are divided into three main institutes. The first one is Citec Energy Storage. We have also nanomedicine department and also surface engineering. In Citec Energy Storage Systems, so basically we start working with battery materials, where we do electroformulations, we work with separators, we work also with electrolytes. Then we have, let's say, a pilot plant, which allows us to manufacture our cell prototypes. So we do the electrode coating, we assemble our cells, and we also do the forming of the cell layer after being manufactured the cell. So regarding to the battery packs, we do our BMS, we work also in the thermal management system, the mechanical design of the battery pack, as you can see here, and also we do the battery boxes, just in case if we need to connect more than one battery pack in parallel in order to reach application requirements. Regarding to the application, we have experience on the electromobility, renewable energies, and also in using second life batteries. So regarding our activity, we have two main working places. So this is the main building, which is located in San Sebastian, and we have a second building in Tolosa, where we extended our testing capabilities. In Fietec, let's say in Donosti, we work mainly in material and components and cell level, where we do here the physicochemical, electrochemical, and physical analysis, ante-mortem and post-mortem analysis. The cell activity, we analyze the performance of the batteries, we do calendar and the cycle aging test. We do also environmental testing using thermal and climatic chambers. Regarding to the mechanical testing, we do some vibration and shock test in order to test our battery modules or even battery packs. And also we have abuse and safety testing. Then the module and pack testing is mainly concentrated in this building. And as we can see here, we have really important testing capabilities. We invested during 2020 around 6 million euros in this laboratory, where here I show you, let's say, our testing capabilities. In this room, basically we do cell and module testing. So basically we analyze the performance of the modules and cells. We do calendar and cycle aging test. We do also the environmental testing, thermal and vibration. We are able also to test under UN 38.3 regulation, which is mandatory for the transportation of lithium-ion cells and modules. And we are able also to do safety test. Here you can see the shaker that we have. This is a dual shaker, which allows us to do the vibration and shock test under UN 38.3 and regulation number 100. And here you can see a working chamber that we have to place inside our battery packs and to test, let's say, modifying the ambiental conditions. Regarding to the testing capabilities, we have around more than 1,000 channels to test at cell level, 75 channels to test battery modules up to 100 volt, and then we have 5 additional channels up to 1,200 volt to test this type of battery packs. So going deeply to the within the BIMIES. In this slide, I'm going to summarize the objectives that the BIMIES should have. The first one, of course, is safety. The BIMIES should avoid this kind of risky situations. We need to ensure a correct use of the battery. We need to diagnose the battery correctly. We need to maximize the battery performance, since this one will increase also the user acceptance. We need also to maximize the battery lifetime, and we need to also to enable the predictive maintenance. As we know, the lifetime of the battery is limited, and if we want to plan, let's say, the battery replacement because the application it requires, it's really interesting to make a predictive estimation in order to plan, let's say, the replacement of the batteries. So regarding to the basic protection of the system, basically the BIMIES has to measure cell voltages with redundant system using different hardware and software tools. Redundant system because we need to check that the measurement that we are doing, we need to be sure that this measurement is a real one. Therefore, we use always redundancy systems using hardware and software. We need to measure also to cell temperature in order to be sure that all the temperatures are within the maximum and the minimum. We need to measure cell and pack currents. We need to measure pack voltages. We need to measure also the pack insulation level, because low insulation level, it could be really risky to use it. We need to check the correctness of all these measurements, and we need to supervise. We need to supervise considering the cell limitations, voltage limitation, current limitation, temperature limitation, and so on. And in order to implement all this, we need to design, let's say, an appropriate hardware which enables the measurements of all these variables that we are considering in this slide. So now, what about the basic SOS estimation? I mean, the basic ones are the state of charge, the state of health, and the state of energy. The state of charge estimation, normally in the state of the art, is using Coulomb counting, also the extended Kalman filter. The aim of this estimation is to evaluate the available amp hour in the battery. And here you can see one of the examples using the extended Kalman filter. Here we have a battery pack estimation where there are 192 cells connected in series in order to reach 800 volts. And here we are able to see, let's say, the maximum state of charge and the minimum state of charge of the cell that are inside the battery pack. Here we are able to see the state of charge estimation during 24-hour operation. Then also we need to evaluate the available watt hour, which is done by using the state of energy. Also, we need to estimate the state of health, which is the capacity of the battery. As we know, the battery has an unavoidable loss of the performance, and this performance is lost partially with the reduction of the capacity, and therefore we need to estimate. This one we have done using transfer charge method and also the incremental capacity curves. Here you can see during the lifetime how the shape of the voltage is changed during the charging process. From this charging process, we are able to measure the incremental capacity curve, and here we are able to see how the peak value of this capacity curve is being reduced over the lifetime. And we have been able to estimate or to measure the capacity by tracking the maximum value of this incremental capacity curve. We know that the state of charge and the state of health, they are correlated, so it's really important to estimate both of them accurately, because if we have an error estimating the capacity, we will have an error also estimating the state of charge. And this data is also really important also for planning the predictive maintenance, as we will see later on in one of the slides. Another interesting estimation is the maximum acceptable current, which is quantified by a state of function estimation. And this one is really important, particularly in fast charge management. Here in this application, we designed a state of function estimation for an electric vehicle, especially designed for fast charge application. This bus was able to charge up to 600 kilowatt during 5-10 minutes.
Sorry to interrupt you, because we have a technical problem here in the room and your presentation got blocked. So if you can stop sharing and reshare again to try if it works now. It seems that the video was quite slow. Sorry for the technical problem.
Okay.
Let's see if it works now. Okay, we can.
So now I am in the state of function estimation slide. I don't know if you are able to see.
We see a black screen. Let's see if we can wait a couple of seconds or try to stop sharing and share again. Otherwise, we can share the presentation for you.
Okay, I will try once again.
Yes, please.
Do you see?
No, it doesn't work. So we can share the presentation for you here, and you can tell us when you would like to switch the slides.
Okay. So basically now I'm in the slide maximum acceptable current state of function. There are some electric buses.
Yes, is it that one?
Yes.
If it's correct, Mikkel, you can go on. Thank you.
Yes.
Sorry.
Okay. Okay. So sorry for this technical problem. I was talking that we designed a state of function estimation that was able to manage a charging process up to 600 kilowatt during 5-10 minutes. So this estimation, it checks cell voltage, state of charge, temperature and current, and will consider this value to estimate the state of function. So basically, this algorithm is identify the weakest cell of each pack. It identifies the weakest cell of all the system. It sends the minimum value to the ECU of the application, and then we send this value to the charger following the ISO 15118, which is the standard one. Here you can see in the right side how the voltage of the maximum cell is reaching the 100%, not exceeding this value, and keeping the cell always within the safe operating area. In the right side here you can see string currents. I mean, this one is normalized, but here we are charging each string around 200 amp. Then we reach the maximum value, and then a CV step is implemented in order to maximize the energy that we stored inside the battery. Here you can see one example, which is the depot station in Amiens, where there are around 50 electric buses. You can change, please, Evelina. Okay, so now we go to the advanced state of X estimation. The first one is always safety. New safety regulation will be released in the upcoming months, let's say. The Chinese one, which is the HEAT Year 20, and the regulation number 100, version 3. So this regulation, they define a minimum safety period from the instant that you trigger the alarm. The BMS identifies an unsafe situation, and between the triggering of the alarm and the event, there is a minimum period, which is around 5 minutes, depending on the regulation. Therefore, new sensing is required, and in i-HeCoBatt we are working in developing new sensor where we identify the hydrogen release and also CO2 gases, the release of CO2 gases sensor, in order to provide this information and trigger the alarm as fast as we can. So also the pressure is increased during the event, so therefore the strength sensors could be used in order to measure this event, and the CAN sensor that meets these new standards. Here you can see, for example, the evolution of the hydrogen release, the increase of the temperature during a thermal runaway event. So in the next slide, what we are trying is to maximize the lifetime. I mean, we need to have batteries that could work longer time. Therefore, the BMS should use the battery in a strategical way, avoiding those aging mechanisms. In this sense, lithium plating is one of the most important aging mechanisms. The aging is induced when the anode voltage is below to 0. In the right side here, you can see in red the OCV cathode voltage, the full cell voltage, which is in blue, and in yellow, very close to 0, you can see the anode voltage. As you can see, at the beginning of the charge, there is an anode voltage around 1 volt, and this voltage is reduced during the charging process. And at the end of the charge, we may have negative values for the anode voltage. Therefore, it's really important to track the evolution of this anode voltage and to avoid these negative values in order to avoid lithium-ion degradation mechanism and enabling a longer life cycle for this battery. This event occurs during the charge, especially at high C rates and at low temperature. So the anode voltage projection, the way the negative voltage will avoid this aging mechanism. and the state of function should consider this anode voltage as well as to limit the charge as the current rate. So if we go to the next slide, i-HeCoBatt is also working in different Horizon 2020 projects where we are developing new sensors. For example, in Spartacus project, we are developing new acoustic sensor in order to estimate the state of charge. They have shown their capability to measure the state of charge. And in Spartacus, what we have seen is that if we inject, let's say, an acoustic current wave or a signal, and we measure the time of flight between the emitter and the receptioning of this, here we can see that there is a very big correlation between the state of charge and the time of flight. Therefore, we think that this sensor could be used for measuring the state of charge rather than estimating. Also, we are working in Cobra project where we are, let's say, using strain sensors, also impedance spectroscopy, in order to measure cell deformation. And as we can see here, and we will see in the next weeks, since we are testing right now, how are correlated the strain of the cell and the state of charge of the battery. However, what we can say that these solutions are still expensive. The TRL level that we have right now, it's quite low, between 5 and 6, and therefore we need higher level of maturation. And what we can say is that i-HeCoBatt has an ongoing research on the mentioned projects. So in the next slide, the idea is to show you the validation platform that we designed. Of course, where we developed new BMS software, it requires very long testing time. So we need considerable human material and, I mean, in general, a lot of resources. So therefore, the virtual platforms using virtual BMS and so on will enable the automatization of this testing and hence saving all the resources required for BMS validation. So basically, in this one, we are able to test cell or module level. Then we have a measurement unit which will take the analog measurement and will transform in a digital measurement. This is going to send to a virtual BMS where we are executing our own code in order to estimate the state of function, event supervision, messaging, and test control, and we'll calculate, let's say, the digital set point to a cell tester or the module tester. And then the tester converts the digital set point in a real value in order to test, let's say, the cell or the module that we are testing right now. Also, we need to enable a post-processing in order to analyze posteriorly the test that we are conducted. And as I have said, it is applicable to cell at module level in different development stages. So the next slide, and I think is the last one, is the predictive maintenance. So as we know, lithium-ion battery exhibits an unavoidable aging. Depending on the application, it might require an intermediate battery replacement, maybe not for a private user, but yes for heavy-duty applications, depending on the battery type, depending on the route, depending on the warranty that we are offering. We will need a replacement, and therefore the rule estimation could provide estimated battery replacement date in order to plan it. Here we can see, let's say, a plot where we have, let's say, an SOH estimation, and using particle filters, we were able, let's say, to make a prognosis with a really high accuracy and giving us, let's say, the probability that we have to happen this end of life for certain SOH. So also correlating the working histograms, temperature and current versus the state of health, this information could be used to add to the existing laboratory agent data. So to finish, I mean, this was my presentation. So if you have any question or comment, you can ask, and I will be glad to answer. And also you could contact me using the email address that you have in this slide.
Thank you very much, Mikel, for this very interesting presentation about BMS that comes complement also yesterday's presentation about i-HeCoBatt project. Yes, we invite you to stay here connected to answer to the question that we will have time at the end of the block. So I'll now give the floor to our next panelist, Dr. Luis Trilla Romero from i-HeC, the Catalonia Institute for Energy Research, who will give us a presentation about the X-in-the-loop techniques for rapid prototyping of BMS. Thank you.
Thank you, Evelina. I think the presentation is coming. Well, hello, good morning, everyone. Okay. Well, as Evelina said, I'm Luis Trilla, I'm a researcher at i-HeC. I'm here on behalf, thank you, of the Marvel project, where we are leading the BMS development. Okay, let's see. All right, excellent. Let me provide some background on the Marvel project. Well, it's actually from the same family of the project that is going to be presented right after me, the Project Liberty. So we are targeting the same objectives. In particular, here we have, different type of, yes, thank you. Different type of nuts, okay, of objectives. From the mechanical side, we are targeting a light battery pack, actually acting on the housing, for instance. Also providing a design that facilitates the assembly and disassembly process, important for second life, recycling, and so on. There are some innovations also in the validation process of the battery pack. As you can see here, we are developing some system called electric vehicle in the loop. But in particular, we are going to focus in this presentation on the battery management system. And, the strategies that we are going to use for the rapid prototyping of the system, in particular using the X-in-the-loop solutions. And, well, I have to say it's a project started a bit more a year ago. So, well, I'm not going to have any experimental results to show, but at least I'm going to give an overview of the work to be developed and the strategies that we are proposing in order to reach the objectives. Okay, perfect. Let's see a little bit more in detail what is what we are proposing for this new BMS. Well, first is the wireless communications that we want to implement. Well, it can, of course, save some weight and some complexity in the wiring harness and so on, but it's particularly important in this case for the automated assembly and disassembly process. It will facilitate a lot to take this step. There's also the development of a data-driven model, not only for increased accuracy, for state estimation and so on, as was explained previously, Mikel, but it can also help to give some predictive maintenance, for instance. Also, we are going to go for cloud connectivity for the BMS. This is very linked, for the previous step, data-driven model. Typically, they are quite heavy, computationally speaking, so part of all of it will be running in a cloud, but also it's linked to the next directives, in particular for the battery passport. We are including additional sensors. Also, the previous presenter was saying there are new sensors that can provide important information about the status of the battery, and a design that is modular and scalable, so in different voltage levels, different battery sizes, and so on. But, well, as you can see, there are a lot of innovations here to be done, but all these innovations have to be validated at some point in order to develop a prototype. It is a problem when you have too many changes and they are all happening at once, at the same time. From the engineering point of view, it's always very complex. and also physical validations, as was explaining Mikkel from CDTech. Well, it takes a long time, it requires effort, time, and it's quite a problem, in particular when projects are limited in time. And, well, as you may know, if you have to develop, for instance, a BMS, the first part of the project is definition of requirements, architecture, and so on. And in the last part, you have to work on the integration in the battery, validation of the system. So you actually have a narrow window of time to develop all this system. And in particular, when the TRL is high, this is quite challenging. So rapid prototyping strategies are quite useful and appropriate for this kind of situations. We are going to explain a little bit, step by step, what we are going to propose here. In the first step, we are working with models and algorithms. Okay. What we do is, well, this strategy is just cell in the loop. We can connect several cells in parallel and develop a model that is also running in parallel, so we can validate if the model has the appropriate accuracy, the state estimation is providing a good result. But if they are working in all the operational conditions that we are proposing for the, well, for this kind of chemistry, in the battery in particular, and this includes first and second life operations. Okay, we can well, modulate temperature, C rate, state of health using different aged cells, and this is something that we well, we will use to accelerate the validation of this part of this important part of the software that will be the next step. Here, then, we have the overall control strategy, all the control logic. This includes, well, the thermal management, for instance, of great importance, as was explained yesterday by i-HeCoBatt and Mikkel also, but also the balancing strategy, integration of the sensor, also the data sharing internally, all the maneuvers, if you have to, well, open, close contacts in different situations, so on. And what we do is to prepare a mock-up of the module. It is better if it's the real module, but okay, sometimes it's complicated, but you can have the sensors, you can have the contactors, you can have the cells, and you can prepare, connect it to your real-time simulator, and then evaluate all these eventual situations that you want to take into consideration for your control system and, well, analyze what are the results. Also, in a kind of, let's say, matryoshka strategy, we are using the previous step as part of the next one. So, in the next step, we are incorporating the model and the control system that is validated, and now we have here the physical part, which is the wireless communications. This is also important to validate because in wireless communications, we'll just have different data transmission speed, bandwidth, maybe you have some package loss. You have to evaluate all these eventualities and check how the system will behave in your control logic or your algorithms if some information is missing, if there's some problems with latency and so on, and also from the physical part. You have too much signal attenuation, for instance, or rebounds of the signal or any physical problems, and you have to, well, change the frequency and the power of the signal and so on, try to adapt to the actual reality of the system. Well, here you cannot see it, but it's also important at this stage to evaluate what is the cloud connectivity and possible cybersecurity threats. So how the system will react if somebody is hijacking the connection and feeding the wrong data, for instance, or if you lose connectivity, or, well, several problems that can happen, and you need to evaluate and validate that the robustness of your design when facing all these threats. And here we come to the final step. This is the well-known hardware in the loop. This is what everyone understands by the hardware in the loop. We have already validated all the other components, and now what we are doing is working the other way around. We can develop our physical BMS, the PCB that you can see here. There can be several, there can be a structure master slave or distributed BMS, it doesn't matter. And all the rest, all the battery, in this case, is what is not real, is simulated. So what we can do here is having the physical form of the BMS, including the communications, wireless and so on, so it's acting like it's in the real environment. We are emulating the battery. The aim is, well, to validate the operation in all the scenarios that we want, and this can include different types of vehicles, types of use, environment conditions, also degradation levels, also including stationary applications, if we want to evaluate second life, for instance. But also, the most important one is that we can feed synthetic data. And, well, we can replicate several faults. So we can evaluate how the system will react when a cell is failing, but also a sensor is failing, if the cloud connectivity, if there are some if there are some problems with contactors, with maneuvers, with any problem, we can replicate it. And then we can evaluate how the system is reacting. This is very important because, well, as also the previous presenter was saying, and probably the next one, safety, it's quite of importance here, and these systems are very complex. As I was saying, we have to development in a very short time, so we have to, well, to take advantage of these new strategies that we can exploit in order to accelerate all the deployment of this new technology. That is all from my side. Thank you very much for your attention, of course.
Thank you very much, Luis. And I now give the floor to our next panelist, Egoitz Martinez Lacerna from i-HeCoBatt. The floor is yours. I didn't break it.
Hopefully not. Okay. Well, in the meantime, thank you all for attending today, and thanks especially for the organizers for inviting us today. It's a pleasure to be present again on an event of this kind and well, to explain you and disseminate our insights on liberty. So as I was presented, I am Egoitz Martinez Lacerna. I'm doctor and researcher at Ikerlan Technology Research Center in the Basque Country, also very close to CDTEC in the San Sebastian area, and particularly coordinator of the Liberty Project. And well, as the title says, and similarly to what Luis just explained, we don't have so many results to be explained today, so I will mainly present our goals and how we are tackling different objectives that we have in the project, and especially some key innovations, at least on the conceptual level. So this one will be the outline of the presentation. We'll just start with a short project introduction with the overview, the goals, shortly our mission, some facts and figures, and the work package structure. And then I will present some of our key innovations. We have quite many, so we will just focus on some of them. And finally, just a very brief word on the i-HeCoBatt cluster, of which the Marvel project is also part. So well, Liberty stands for Lightweight Battery System for Extended Range at Improved Safety. And we have 5 main objectives. We start from a benchmark vehicle that in our case is a Mercedes-Benz EQC vehicle. And the goal is to develop a brand new battery pack that we will finally integrate on a demonstration phase in this vehicle. So the goal is first to achieve a range of 500 kilometers on a fully charged battery pack. To achieve a shorter charging time, we are targeting just around 18 minutes for fully recharging a battery pack, in this case with up to 350 kilowatts during the charge phase. Then, of course, as you just mentioned, to achieve an ultimately safe battery pack, which is crucial for a demonstration phase of this kind and also for the automotive sector, of course. To reach a longer battery lifetime compared to what we currently have in the benchmark vehicle, and finally to meet all these goals in a sustainable way and taking a look on the whole battery pack cycle life, or life cycle, sorry, also considering potential transfer to second life. very shortly, our mission is to build next-gen sustainable batteries, integrating cutting-edge technology and innovations from the component level into the system level. That will be reached and demonstrated, hopefully, in the final demonstration of the whole battery pack. We are 16 partners from 7 different countries, quite some big names in the picture in there. The coordinator, it's myself and Nikedan as a whole. And well, we just started in January in the last year, and the project will last for 42 months. So we are just close to the middle of the project, but still on the requirements definition design phase. And just to take a quick look on our work package structure, we just follow the typical V-shaped design methodology, starting from work package 1, requirements, design criteria, etc., then moving on to a conceptual design of the subsystem level, and finally defining or setting the next steps for component level designs in work packages 3 and 4, where we will design all the components, build them, including casing, BMS system, etc. And finally, in the right side of the picture, we have 2 work packages. Work package 5 mainly meant to define novel testing procedures at every level, component, system, subsystem, and finally in the vehicle level. And work package 6 actually tackles the carrying out such tests. And on top of all that, we have a work package fully focused on LCA analysis, total cost of ownership, life cycle inventories, etc. So just supervising all the designs we do from the sustainability and cost point of view. So moving on to some of our innovations. Unfortunately, my picture is hiding most of them, so I will say it just out loud. We have in there the objectives just for convenience, but the main purpose in here, the car is nice, it's the part you can see, but I would like to talk a bit on what we are actually doing in the project. Oh, perfect, thanks. So we're starting from the casing. We will have an adapted casing for our case. The shape will be pretty much the same, but we will change the top and bottom covers just so it can be more lightweight, let's say. Then new cells, a new cell configuration, targeting a cell-to-pack approach, at least to the possible extent with the boundaries we have in the vehicle. An immersion cooling-based thermal management system, new electronics, a novel integrated circuit, novel BMS, adapted also to the immersion cooling concept, and new pressure sensor also for safety purposes, new advanced state-of-X algorithms, battery passport, cloud connectivity, remote troubleshooting, all this fancy stuff you can imagine on a vehicle of this kind. So I will just start with some of the innovations that we are bringing. I'm not allowed to show so many results so far because we are fully immersed in the rock and roll phase and the design of every component, so it's been quite a hard time. By the end of this year, we will probably have more results and all the components will be already on the manufacture phase. So we will be closer to showing something, but at least the conceptual approach so that you can know what we are targeting. As for the thermal management system, we are going for a immersion cooling based thermal management system. In this case, it's monophasic. So the idea is that the cells will be partially immersed on a dielectric fluid, and then we make this liquid or this dielectric liquid flow through in a closed circuit. So we will absorb it, cool it down, and then spray it over the cells. And the idea is that we will have some nozzles integrated in the battery casing in our design so that we can cool the cells and increase the heat transference. Then we will also have some filters, etc., so that we can avoid any particles or any dust, any issues with the aging of the electric itself. We already have some tests, and we are working on the integration on the whole battery pack. And actually, we are carrying out many different tests on dummy cells and also on small stack level demonstrators so that we can prove how the liquid flows, if we have any viscosity issues, how the thermal transference is working, etc. So this has been quite a topic for the time being because it's actually, it has a strong impact on the whole design of the battery pack. Apart from that, also very strongly related to the immersion cooling concept, we will have an active safety system. So we will have our cells encapsulated somehow in a group of cells. And this concept will work in parallel with immersion cooling so that we can avoid having any safety issues in case of a thermal runaway event. So the idea is that the immersion cooling will help to mitigate the propagation, the thermal propagation. But apart from that, we are also exploring if other materials can also collaborate on this mission. And for that, we will have two different elements, an active one that is like the walls you can see in the surroundings of the cells that are somehow aluminum materials with a liquid inside that boils. It's a two-phase fluid that boils in case of a thermal runaway event, and in that way prevents the cells from heating that much. But even if that happens, we have a passive layer, fire retardant material, in this case, that avoids the thermal propagation from one group of cells to the other. Just some additional details on the pictures on how it actually looks like. But the idea is that we will have to check how these two elements, the immersion cooling system and the active safety system, actually work together, try to minimize the need for an active safety system, or evaluate at least how this can be complementary and work together, just to avoid any safety events. This, of course, has also some important impacts on the thermal management system and also on the cell-to-pack approach that we are targeting. But the idea is that at some point, if this can be industrialized, this can be minimized or even eliminated in case the immersion cooling system is already doing the work and avoiding any thermal runaway propagation. We are also working very strongly on the battery management system and the high voltage electric system. As you can imagine, having an immersion cooling concept, we will have to realize the whole electronic systems and all everything that is on top of the cells needs to be adapted so that the liquid can flow and can be adapted to the immersion cooling concept. In this case, we have integrated our bus bars. This is only preliminary, so we are still adapting a little bit and shifting a few things, but it will pretty much look like that. So the PCB that you can see in there is the slave for the BMS system, and the bus bars are also adapted so that they can allow to flow the liquid, but also contribute to heat, to cooling down the cells from the taps, let's say. Well, the goal in here is to maximize energy density and also to allow a potential cell-to-pack approach. One interesting feature is that we are basing our BMS in the Fox BMS2 that the Fraunhofer Institute is developing, and well, actually, from Mikeland, we are also contributing in that part, but it's an open source BMS platform that can be publicly used in European projects of this kind or any other projects that you may have. Another topic, another key innovation that we are bringing in here, and particularly from Mikeland, we are very strongly involved in this part. We've been working for some time, from some years already, on advanced data-driven algorithms for lifetime prediction, for any other purposes related to in the batteries field. And now we are bringing in here some concept for a state of X estimation. The idea here is that we can have a quick model development phase so that when we have to change from one cell to the other, or just different generations of a single cell or different chemistries, we can do it in a pretty quick way and with a very reduced experimental burden, because normally you need some characterization, aging, etc., just to be totally sure that your algorithms are working fine. So our solution for that is to use data-driven modeling techniques. In this case, we take advantage of field data that we can directly get from the vehicles already deployed in the roads to improve iteratively our algorithms. And the idea is not only that, but also to have the possibility to apply some transfer learning techniques that we can use once we have generated a model already working well enough, let's say, to get that knowledge and to adapt it to new cells, new references, new chemistries in a rather quick way. The idea in here is, well, the benefits are that we can have an increased accuracy, which even becomes better and more reliable as we get new data. That's particularly interesting if you can merge all the data from different vehicles, different applications in one, in the same resources or database. An improved performance at unobserved conditions, because if we have vehicles at different locations, we can also observe a wider range of operating conditions. And as I said, just reduce quite a lot our experimental burden. If you are interested on these topics, some of my colleagues will be presenting more details in this regard on the state of charge estimation in the EBS 35 in Oslo next June. So just catch up with them, and they will be happy to talk with you. And finally, we are also working on the battery passport concept. This was it's quite a topic in the last years, and we are making our slight contribution in this regard, especially with the dynamic data we can get from field operation. The idea is, well, that the data we generate during the vehicle operation can be processed, cleaned, mined, wherever we want to do with the data, before storing it in a certain passport, so that it can be useful for any services we can imagine for the vehicle itself, like remote troubleshooting, predictive maintenance, any other service related to the data of the vehicles that we can imagine, but also and especially for a potential second life use, so that second life stakeholders can take that data and benefit for that before deciding if a battery is eligible or not for a potential second life use. And well, that's the innovations that I wanted to present today. Just before concluding, a few words on the i-HeCoBatt cluster. All the LCBAT 10 projects in the 2020 call that were finally granted, we have merged into a i-HeCoBatt cluster in which Albatros, Liberty, Ilios, and also Marvel, of course, are taking part. This cluster is meant to disseminate our results, but also to promote some technical discussion among the different projects we are taking part. We already built 4 main technical subclusters meant or focused on sustainability, testing, BMS, and we are about to launch right now the 4th one on battery modeling. And we are already running some meetings and holding some technical discussion. The idea is that we can get into common approaches, find synergies, and potentially provide some outcomes to the battery community, and also potentially to upcoming European projects, so that we can use some guidelines or some white papers on how we approach many things in this regard. The LinkedIn page was, this is wrong, it was just published this week, so if you are interested, please follow us, and we'll be happy to engage with any other European projects, any other clusters, etc. Actually, we held just today a meeting with Leap Planet, for example, so we are already closing relations with many other clusters and projects. And well, just to stay tuned for upcoming events, workshops, white papers, guidelines, many different stuff that we are preparing during the second semester of the year. And that's pretty much it from my side. If you have any questions, then in the questions block, I will be happy to answer. Thanks for your kind attention.
Thank you very much, Goetz, for your presentation. Since we are a little bit behind our agenda, and we also have a surprise before the coffee break, we'll just take one question from the audience. I think that on slide we don't have any questions. So are there any questions from the audience in the room? If you didn't have time to think about the questions, I think you can wait for the coffee break. Oh, you have a question from Mikel Arrinda. You have to switch on the microphone. Hello. Let's wait.
Hello. Okay. Thank you. We had some technical issues with the presentation of my colleague Mikel Oyarbide, and if it is possible, if he could show us the installation
of course.
Mobile, it would be nice.
Of course. Mikel, could you hear us?
Yes. So what was
Perfect.
The request of Mikel? Just to show...
The slide with all the installation in mobile.
Ah, okay.
Yeah.
Is it working?
We are working on that. Just one second.
maybe Dimitri can show if you told us the slide number.
It's the number 7, so I will stop sharing my screen.
Sorry for the waiting. We're just sharing the slide 7 of your presentation. Okay, now we can see it.
Yeah, so sorry, because I was not aware of this loss of image, and I was talking, and I wasn't. I haven't realized that
the problem is us. No worry.
Was frozen. So yes, so basically what I was telling is that here in Mobile we extended our testing capabilities. So the equipment that we have for cell and module testing, it's around between, considering the testing capabilities that we have here in Donosti and what we have in the second building in Mobile, is around 1,000 channels for STFL testing. We have around 75 channels in order to test the modules up to 100 volt. We have also five channels to test a large battery pack up to 1,200 volt, and each one consists of 250 kilowatt. Regarding to the ambiental testing, we have 2 walk-in chambers where we can place all the battery pack or even all the system, all the energy storage system. And for mechanical and vibrationing, we have a dual shaker, which is able to conduct the UN38.3 test and also to test under regulation number 100, which is mandatory to pass this test in order to commercialize, let's say, the battery pack. So yes, I mean, this is a kind of short introduction, but of course, if you have any question or any doubt or any suggestion, we will be happy to answer using the email that I was showing during the presentation.
Thank you, Mikel. And the presentation will also be shown on the website of the event. So thank you very much for showing again. Again, sorry for the technical issue. I think it was a connection problem. So if there are... Thank you very much, Mikel, for being with us. And yes, so if there are no more questions and questions can be asked during the break, I invite you to join us to the coffee break. But before rushing upstairs on the terrace, we have a little bit surprise for you. From the i-HeCoBatt project, we have an electric vehicle to show you downstairs, just at the entrance of the hotel. So you're more than welcome to join us downstairs to see the vehicle, and then we can all enjoy a coffee break for 10 minutes. And also to take a group picture, so do not run away. Thank you very much to all of you. invite all our attendees to take a seat. We're starting again. Thank you.
Hi. Let's continue now with the third block of the day, which is on the green mobility use experience and infrastructure challenges. So we have for this purpose 4 excellent speakers. 2 of them are here with us, and the other 2 are online. So let me to introduce them. We have here Eduardo Rivero from the Automotive Technology Center of Galicia in Spain, Miguel Zarzuela from the Circe Technology Center in Zaragoza in Spain as well. And then we have online with us Evangelos Karfopoulos from the Institute of Communication and Computer Systems in Greece. Hi, Evangelos, are you there?
I'm there.
Okay.
Can you hear me?
Well, yeah, welcome. And then we also have with us Carlos Almeida from EBIO. Hi, Carlos. Are you there? You're mute, I think. Well, we will try later. So I would like to express our gratitude to all the speakers for accepting our invitation and be here to share with us their knowledge and progresses. And without further delay, I would like to introduce our first speaker, Eduardo Rivero. I invite you to present your speech on the, well, he's the responsible for the electric vehicle unit in the Automotive Technology Center of Galicia, the CTIG, and he's talking us about the electric vehicle market status and perspectives. So, Eduardo, the floor is yours. Thank you.
Okay, hello everyone. Thank you for the introduction. I will try to speak close to the micro. Okay, I think this is okay. Well, I would like to thank the invitation of the organization. It's a pleasure for me to be here with you. I want, I don't know if this work. Okay, okay. I want you to direct your attention towards this first image. This is an island in front of Vigo city. It's in Galicia, in the northwest of Spain, in the border with Portugal, in Atlantic Ocean. It's in the corner of Europe, far away of everywhere. Yes, that's true. But here is the perfect example of the combination between the automotive industry, the mobility, and the environment. Here is located the largest factory from Stellantis Group in Europe. It's a factory that manufactured every year 400,000 vehicles, and around this factory there are more than 100 suppliers, providers, component suppliers, tier ones, and one R&D center, CTIG, that I'm working currently in this center, and this center started the activity in year 2002. Let me introduce the key numbers, the figures of CTIG. 900 persons working currently. The prevision is to reach 1,000 at the end of this year. 80% are engineers. 70 million of investment, accumulated investment, since year 2002 until now. And the 65% of our turnover comes for international activity. International activity, mainly French market and German market. The last important point maybe is that the 50% of our turnover is directly with the constructors, with the OEMs, the car manufacturers. And the other 50% comes from the tier 1 suppliers. Okay, we'll try to. Okay. CTIG is a non-profit entity. It's a private, independent center focused on the automotive and mobility sector. And our RD activity responds to the challenge of the vehicle of the future, to be safer, smarter, connected, autonomous, and sustainable. And here you can see some pictures or some images, some activities of our center. In year 2018, we start with the active battery lab. It's a specific laboratory in order to perform testing and characterization with big battery packs. We can manage 1 ton of battery pack with combining tests. We have a big volume climatic chambers, combined with multi-axial shakers, combined with cooling units, liquid cooling units, also with thermal, to reproduce thermal cycles, and we can perform a reliability test in this laboratory. Thermal, electrical, and mechanical test. Here you can see an e-axle test bench. This facility is focused to develop or to optimize the e-powertrain, the complete e-powertrain of the vehicle. We are talking about the battery, the inverter, and the e-motor together. We have also some tracks in order to develop other systems, autonomous vehicles, to validate or to reproduce urban environments. And yes, more or less is our main activities. Okay, let me pass for the following. Okay. First, I will introduce a general view of the sales of the EV world market. Then I will talk about the OEM perspective. Third, I will talk about the strategy of the OEMs to reach the objective that in 2030, the 30% of the sales will be electric vehicles. So I think that the industry has a specific strategy, and we talk about that. The 6 million electric vehicle sales last year, 2021. The global stock is 16 million electric vehicles. The trend of this curve is exponential. Maybe in this graphic you can see that the mainly market last year it was Europe and China. So Europe is increasing the market thanks to the incentives and thanks to the governments, but also for the effort of the industry and for the investment of the different OEMs. So the prevision is that the government kept the fiscal incentives that allows to maintain this tendency. And maybe it's important to remark that the EV sales are increasing. Meanwhile, the car sales, the car market is decreasing. So I think maybe in the following years, this tendency continues. The private sector perspective. The 90% of the OEMs are launching a new models, a new vehicles. 18 of 20 largest OEMs has a strong commitment with the electrification and with the mobility. And I think that with this commitment and with this offer, the sales will increase. Volvo, Renault, Opel, Ford Europe will announce that in 2030 will only assemble electric vehicles. General Motors, the same in 2035. Volkswagen Group, Stellantis Group, it depends of his position in the market, has a different strategies, but in Europe, for example, the 17% will be electric vehicles. In USA, Stellantis, the 35%, in China, Volkswagen, the 50%. So I think that the commitment is clear. New brands appear, of course, Tesla, Remark, but specific new brands for the OEMs appear. Polestar for Volvo, Cupra maybe for Seat. So with this commitment, we estimate that in year 2025, around 50 million, between 50 million or 70 million of cars will sell in 2025. Okay, I think that there are three common pillars in the strategy of the industry, the OEMs, with the OEMs. The first one is developing a dedicated platforms. Each OEM dedicated a EV platform for mid-range vehicles, for premium vehicles, for light-duty vehicles, commercial vehicles. I will talk about that in the next slides. Also, the second pillar is the relationship and the joint venture with the players, with the battery manufacturers, with the e-motors constructors, with the power electronics companies. The OEMs start to create a partnership, a joint venture with these new players in order to bring the know-how, in order to bring the knowledge. And the third pillar is the software. I think the software is becoming more relevant, more important. Software for the control of the inverter, for instance, or for BMS, or for BMS, the software for charging and recharging the battery, the fast charging, the vehicle to grid, the new uses of the vehicle as a grid. So, and finally, the software for infotainment, for connectivity. So I think it's the third pillar, and it's an important point. And the industry must adapt to the change of the market. And here there are two examples. The market increasing the demand for zero emissions of commercial vehicles for fleets, and now the OEMs will release more light, mid, and heavy duty vehicles, and also change the paradigm. So the business model, I think, is a technological market. The mobility as a service is an important topic the autonomous driver, the vehicle to grid, and some possibilities. So I think it's important to adapt to this new market. Here, the relationship with between the OEM manufacturer and, for instance, the battery manufacturer. You can see that there are a strong relationship. The gigabatteries are necessary to allow the introduction of the electric vehicle in the market, but not only one gigafactory. Maybe for each OEM, for each market, Europe, America, China, maybe each OEM needs 2 or 3 gigabatteries. So I want to remark here, for example, the ACC company, automotive cell company, that is 100% European. It's a joint venture between the Total SAF group and Stellantis group. And last year participated the Daimler group in this company with the 33%. So it's a European company that is projecting some gigafactories in Europe, one in France, one in Germany, and another one in Italy. I think they announced that. Yes, it's an example, no, of the relationship between the OEM and the manufacturers. And finally, a concluding remarks. No? Here you can see in this image all the important topics, the vehicle production to electrify the market, the safety, the connectivity between the infrastructure, the vehicle to vehicle, vehicle with infrastructure, the infrastructure for charging points. So it's important, the mobility, not only in the last mile, in the sea, outside of the city. So we need to reinforce the infrastructures, the research infrastructures in order to reach this mobility. But of course, there are challenges. Yesterday we talked about the supply chain issues, chips, rare earths, batteries. Regarding the batteries, the charging time, reduce the charging time, but without reducing the lifetime is important. Increase the battery range, the smooth operation of the extreme temperatures, the new designs for recycling the batteries. So regarding the batteries, there are some challenges. Regarding the infrastructures, it's important to deployment an extensive charging network. As I said, the heavy duty need superchargers in order to accelerate this introduction. And in my point of view, the new software developments are the key point. Mobility as a grid, vehicle to grid, fleet management, smart charging, over-the-air software updates, big data, and digital twin, infotainment. I think the software is the challenge to adapt the industry, technological industry. So I have finished with this message. But it's clear that the industry has a strong commitment now for the electrification and with the mobility. And I think that the infrastructure that my colleague will talk in the following presentation now is really important to reach this objective. Thank you very much. If you have any question, I'm glad to answer. Thank you.
Well, Thank you very much, Eduardo, for this overview on the EV market. And well, now our next speaker is Miguel Zarzuela, which is project manager at CIRCE. And his speech is on e-mobility adoption, a success story from the INCIT EV project. So please, the floor is yours.
Thank you very much for the kind introduction. Glad to be here today, for having been invited to this event. Today I'm going to talk about Insight EV. This project is a very large project coordinated by the CIRCE Foundation, but it contains a consortium of 32 partners with a 19 million investment, of which 15 million comes from the European Commission. This project is focused on the user needs in order to develop innovative charging solutions that solve or will solve the actual problems that the users are facing in regards with electric mobility, with the ultimate objective of foster EV sales in Europe. I will come later, but we have 7 demonstrators across all Europe, so they cover all kind of innovative charging solutions, and I believe that you will interested at least in some of them. This consortium, it comes of 3 OEMs, several universities, technological centers, public administrations, DSOs. So we are very skilled in to cover all the activities that we are developing, which I can assure you that we are doing a lot. Let me start with a short question. Have you arrived today or to Valencia by the means of an electric vehicle? Electric trains also count. If the answer is no, very good. Electric motorcycle also counts. Here in Valencia we have some of them. Our goal is to know why you have not used electric vehicles to arrive here, and what can we do in order to solve this issue, to promote this new zero emissions mobility. As you know, and Eduardo has introduced it, EV vehicles sales are on the rise. In Spain, we are reaching about 8% of total sales with plug-in vehicles. In Germany, last December, they reached about 35%. You know that in Norway, they are reaching almost 98% of plug-in vehicles. So we are right now talking about this innovative product taking now the early majority. So we have crossed the cans, which is the moment that decides if a technology is going to succeed or not. So we are taking now the early majority, and I would like that the audience that this project will reach at some point will ease the uptake of this electric mobility. Let me showcase the main objectives of the project. As I have told you, first leg of the project, we are analyzing the EV users' needs and preferences, also to know their gains and pains in order to develop new technologies that will solve or will ease the use of electric vehicles in their daily life. To doing so, we are focusing here in 2 main technologies. One is inductive charging. For the ones present face-to-face in this meeting, have been able to see the Zoe vehicle that we have downstairs equipped with the coil that our colleagues from Vedecom in France, in collaboration with the group Renault, have developed. So this wireless charging is able to charge up to 90 kilowatts a Renault Master van that will be run test in Paris. But the urban demonstrator of Paris will be able to charge up to 120 kilowatts at the same time for vehicles. These demonstrators, as I will tell you later, are able to charge on a static base, therefore without movement, without cables, but also reaching highway speed up to 130 kilometers per hour. We are also developing low power and high power B2G chargers with grid capabilities in order to communicate with the DSO and TSO to fulfill the best management of the grid when the vehicles are charging, and also to even improve the quality of the grid while the vehicles are charging. B2G has been commented during today and yesterday's session, is a technology that will be used in the next years and have a really huge potential in order to integrate the vehicles into the grid, and also to enhance the use of self-consumption systems and to use the battery as backup for smart grids. We are developing also a decision support system for mobility planners, taking into consideration the EV penetration sales and also the infrastructure penetration in order to mobility planners plan what are the numbers of electric vehicles and the power and its impact in the grid that they need to develop plan for the cities and regions. Of course, we are also obtaining real data of the new use cases to develop new business model for all of them. We are right now at the half of the project. This is a four-year project. We have ended right now the theoretical development of all the charging technologies, and we are now in the last phase on the engineering of the prototypes in order to be all of them developed during this summer or at the end of this year. We'll have the whole next year for the operation phase to obtain efficiency and all the results, also the user perception of these new technologies on the use cases that will take place around all Europe. Let me start from the beginning. Our colleague from Zaragoza, BitBrain, is leading the task concerning knowing the user perception about the charging infrastructure. So with different qualitative and quantitative methodologies, we are obtaining the information of EV users and non-EV users about their concerns and necessities concerning the recharging of the vehicles. This is preliminary. In June this year, so in 1 month, we'll have a full disclosure report of what are the conclusions until now. Of course, what we know about the users is that they want cheaper vehicles with longer range that charge faster. But if we extract this into exact points, we have detected that they want to have seamless and reliable charging, so that all available chargers are working and are very easy to work. So they are looking about interoperability and very seamless functioning of payment, as pay as you charge, identification of the automatic identification of the vehicle, or paying with the credit cards, as we are used to do in traditional gas stations. They will like also very fast charging on the highway corridors in order to reduce the charging time when you are traveling more than 400, 500 kilometers using an EV vehicle. And there is a starting need of integrating the EV batteries into the grids. Therefore, a lot of houses here in Spain, we have the lack of having a lot of sun during the whole year. Therefore, self-consumption photovoltaic systems are rising. If you have at your house park 50, 60 kilowatts battery outside, why not using this not only to recharge it with the self-consumption production, but also to use this energy in the hours that you don't have sun in order to reduce the cost of your bill. So for this reason, we are developing also the B2G chargers as an integration point for the vehicles into the grid. From the grid operator's perspective, there is also a new need of using this existing battery storage on wheels to be integrated into the grid. So they really, we believe that in the next years, we will see offers from the grid operators to pay the EV users just to have available and in a manageable way their batteries in order to provide ancillary services everywhere. Therefore, to have active points in which the grid operators can manage the quality of the grid by the using of smart charging or even B2G chargers. As I have said at the beginning, we have 3 OEMs in the project that are helping us in the retrofitting of the vehicles in order to use these new technologies. I will now go through the inductive charging solutions. I will go later with the conductive ones. We have developed, together with BDCom and Renault, interoperable inductive charging system without cables that, by the use of 30 kilowatts coils, allow us to equip 4 vehicles that will be used in 3 demonstrators. This approach of interoperability and to use the same vehicles and the same coils, so any of the vehicles can charge at any of the use cases. So this has been a really complex definition solution to find a compromise operation point for all of them with a good efficiency in all of the cases. As you know, or maybe you don't know, but I will explain very shortly, inductive charge system is composed of a coil that is in the ground and a coil that is in the vehicle. In the case of static charging, we only have 1 coil in the ground and 1 coil in the vehicle. In the case of dynamic charging, as the vehicle is moving around the infrastructure that is above, on the ground, we have to install a line of bobines, of coils in the road. Let me start for the most simple solution, which is static charging. This use case will be placed in Zaragoza. The vehicle that is downstairs will be the one used there. Here we are aiming for a 50 kilowatt charger, but the coil on the vehicle will be only 30 kilowatt, as is the one on all vehicles. But this system allows a misalignment of about 25%. It charges automatically once the vehicle is detected over the charging spot. And we have designed it with a 95% charge efficiency in concerns with conductive charger. This is a topic that has been always behind inductive charging about the efficiency. So the ongoing design, as we are shielding the ground and shielding also the vehicle, the electromagnetic field is very concentrated into the coil of the vehicle. Therefore, we have not too many losses. So we lose only about 5% of the energy in comparison with a conductive charger, which is really good final data. This charger, we believe that the real what we will see in the next years will be a low power version of this charger, about 7 kilowatts, that will be offered as a premium charge for electric vehicles. So we will pay an extra when you buy a vehicle, and you can start this charger without cables for your own parking. So you will benefit of seamless charging at your home. In this case, this is focused on taxi users, therefore to allow them to charge while they are waiting the next customer in the waiting line of a taxi stop. Next system, a little bit more complex. This will be in the city center of Paris. This will be a road of 1 meter coils that will be activated once the vehicle passes over them. So there is a communication between the road and the vehicle, and the coils are activated only when they are over the coil. As you see, we'll have the master van that has 3 coils, that therefore is able to use at the same 3 coils of the ground and to charge up to 90 kilowatts. And the SOE, it will be a replication of the SOE that we have in Zaragoza, will work only on one coil. This system is fully integrated on the pavement, therefore you won't see nothing. In all of systems, you won't see nothing from the user's perspective, but you'll have an alignment system that will indicate you how much are you aligned and how you can improve the alignment. The better alignment, the better efficiency of the charge. This system is prepared to work between traffic lanes, so the vehicle is prepared to be stopped while the lights are red. But what we are developing in the next use case, which is at the outskirts of Paris, in Versailles, in a high-speed track at the BDCom facilities, is almost the same approach, the same vehicles, the same coils, But on the ground, we have longer coils, 10-meter long coils with only one wire that runs along the asphalt behind the ground. And the goal here is to reach up to 130 kilometers per hour at highway speed, therefore to demonstrate this solution for ring roads or highways in which you can charge while you are driving. Here the major problem is, or the most complicated one, is the control of the activation of the coils, because as you can imagine, you'll be only 1 second over the coil, so you have really to act and commute the coils very, very quick. For your information, you have seen downstairs the vehicle. It has, for each of the coils, charger. In the case of the SOGAS, it's only one coil, you have only one charger. This is AC-DC, so it converts the AC input from the coil to DC of the battery. Has a communication with the power, with the BMS of the vehicle, so we can adapt the output of the coil according to the needs or the state of charge of the vehicle. Let me go to conductive charging solutions. This will be a 200 kilowatt charger that will be installed in Tallinn. It has direct communication with the DSO and the TSO using some interoperable protocols, so they can send signals to the charger in order to compensate reactive power or even to reduce the active power if the grid situation over there is critical. This system allows to have a really fast charge of about 15 minutes for the batteries, and also allows the grid operators to interact with the chargers, because imagine that we have 8 of these chargers at the same location, to control or to have signals over there to balance phases, to control reactive power, and to improve the quality of the grid. We have several other demonstrators that I'm not able to showcase all of them, but we are focused also on bidirectional charging at low speed, so about 3 kilowatts in Torino. In Faraofa, we have also one charger of 25 kilobytes. In Amsterdam, we are developing AC bidirectional charging, therefore by using onboard charger in the vehicle. In this case, we are using Ioniq 5 vehicles that the onboard stock charger has these bidirectional capabilities. And we are also developing smart charging algorithms. These we have since beginning of the year, well, this started last year. These are real data of 40 charging points in the Amsterdam area in which we have applied smart charging algorithms. This allows to reduce the load at peak hours. So this is the demand of the charging points, not of the grid. So we can reduce at peak hours the power that the system is demanding in order to delay this charging into the night. This can be more aggressively delayed depending on the user needs. So, but also in case that the user doesn't want to use this smart charging algorithm, he can avoid to use them. But if you are connecting the vehicle around all the night, you don't need to charge faster at the beginning of the connection. So I'm going just about to finish. This is the decision support system that we are developing. As I have introduced you at the beginning, this will work as a cost-benefit analysis by introducing the exact penetration curves that we are expecting on a region or on a city to provide the optimal sizing and siting of the charging points, and also the grid impact that it may have on the grid. We are paving also the standards of inductive charging. As you know, interoperability is also a big topic in all kinds of solutions. This one, at this point, we don't have standards for the power that we are developing. So we hope that with the result that we are developing, the frequency in which we are working allows to create a standard in which all inductive systems will work, therefore to permit all kinds of vehicles and inductive charging systems to be interoperable between them. I will just finish. Our final objective of the project is just to boost EV sales. As you know, we have to be energy independent in Europe, and we'll have to cut the CO2 emissions. Therefore, this project is improving the existing charging technologies in order to allow the user to use these vehicles in the best possible solution with the existing technologies that we have. This is the end of my presentation. If you have any question at the end of the blog, I will be more than happy to answer you. So thank you very much.
Thank you, Miguel, for your presentation, this really interesting and ambitious project. And I am now introducing our third speaker, who is Dr. Evangelos Karfapoulos, which is a project manager at the Institute of Communication and Computer Systems. And he is presenting us another success case on e-mobility adoption from the e-Charge for Drivers project. So, Evangelos, the floor is yours.
Thank you very much. Good morning to everyone. I'm glad to be with you, even at a distance. I'm sorry for not being able to be present there with a physical attendance, but I will try to give you as much as possible as regards the e-Charge for Driver project. I'm Evangelos Karfopoulos. I'm a senior researcher in the i-Sense group in the Institute of Communication and Computer Systems. Today my presentation is to provide you some insights about the e-Charge for Driver project, which is a 4-year life project, which is in the middle, in the second year life of this project. The e-Charge for Driver project aims to design and develop new technologies and services that will foster e-mobility and will improve the charging experience of EV users. Within the project, 12 countries are participating, reflecting the different e-mobility maturity and the different needs and preferences of the users as regards the maturity of the e-mobility. 31 partners are involved with diverse experience and expertise from EV manufacturers, EVSE manufacturers, CPOs, service providers, municipalities, research centers, universities, etc. The solutions that are developed in the e-Charge for Drivers will be demonstrated in 10 demonstration areas in 10 different countries. And these technologies aims to serve the different charging needs in its area. The objectives of the project are 5. Starting with the first one, since e-Charge for Driver project aims to create user-centric solution, and this is the different from the previous European project in the previous years, that we are not only focusing on the efficiency of the technology, but the main goal is to place the user in the middle and identify which are the needs of the users as regards the charging technologies and the charging services. So in this respect, an extended user survey was conducted in order to understand which are the users' needs, the user preferences, user concerns, not only from the EV users, but also which are the anxieties from the non-EV users in order to be able to persuade them to be also in the circle of e-mobility. The next step is to design new innovative solution and user-centric solution based on the outcomes of this survey. And when we are talking about solution, we have 2 directions. The first one is to create user-friendly and cost-efficient technologies for passengers and light electric vehicles. And the second direction is to create interoperable and enhanced charging services that will allow users to have a better accessibility to the charging station, a more efficient and user-friendly charging experience, And the next objective is interoperability. This is the main and the key pillar of any technology and service that should be designed and developed. And interoperability should be ensured as an end-to-end requirement, from the vehicle up to the highest level, which is a roaming platform or a certification authority. This interoperability will not only allow the accessibility of the user to the different charging stations and the exploitation of different services from different service providers and different vendors, but also will allow the provision of enhanced information to the user before, during, and after the charging station, which is something that is missing from the current solution. Finally, the e-Charge for Driver will develop mechanisms and tools that will foster the deployment of e-mobility in urban context in a sustainable and user-centric way. And this will be realized by providing two different tools, a charging point location planning tool, and will propose new tariff and incentive schemes. If we would like to give more details on the technologies, on the e-Charge for Driver solutions, we have three directions: technologies, services, and decision tools. On the left hand, in terms of technologies, we can have two parts: the charging stations and the vehicles. In the upper left part, we have three different charging solutions. The first one is a user-friendly, modular, and containerized charging station with enhanced user interface, which means large onboard screens that allows the user to have information about the charging process, the pricing policies, any incentives, any possibility of participating in smart charging concept, etc. This technology is developed by ABB, and the containerization of this solution aims to facilitate and make quicker the deployment of such solutions in urban context require the minimum civil engineering work. The second solution is a multi-outlet DC charging station for EV, for passenger EVs and light electric EVs, enabling the vehicle to grid functionality. This charging station is developed by Powerdale, and apart from the possibility of serving the charging needs of different diverse technological cars, EVs, passenger vehicles, and light electric vehicles, it enables also the power flow, the bidirectional power flow between the grid and the electric vehicles. The source or the energy source of this power charging station can be multiple sources. We can have flow of energy flow from the electric grids, from a local storage system, from local renewable energy sources, etc. The idea of this solution is to minimize the capex by having a central cabinet where all the power electronics are placed and all the inverters are existing. And then we have separate interfaces that allows the communication and the different communication protocol implementation for the diverse technologies of the vehicles. The third solution is the battery swapping station for light electric vehicles. Yesterday morning, there was a great discussion from the Ms. Costanza Hermanin, representing the Swappable Batteries Motorcycle Consortium, where the battery swapping interest as a raising business use case was discussed, and it was really very interesting. There, three main key points were identified: interoperability as regards the batteries, safety standards, and grid-oriented services that can be provided by such solutions. In the e-Charge for Driver, in this respect, the e-Charge for Driver project designed and develops two different approaches. The first one, that it is developed by SWAB in Berlin, aims to integrate 6 different, at the moment, battery technologies for light electric vehicles by having different compartments in the same charging station. So the user can quickly, in less than 1 minute, can exchange the discharged battery with a fully charged battery. This is important because by this case we can enable and realize the context of storage of battery as a service, which means that the owner can lease the battery and can avoid the high costs of being the owner of such a battery. The second approach is designed by Scutum and will be demonstrated in Barcelona. And the idea is that the whole system of the battery can be removed from the vehicle, and this battery pack is transferable like a trailer, and the battery can be charged either at home or at place, and of course you can charge it in any charging station as well. The final step of the technologies that is proposed and developed is the modified electric vehicles. We have Volvo, BMW, and Bosch that are creating 3 prototypes that enables V2G functionalities by converting the power electronics within the car, as well as they are updating their vehicle controllers in order to support the ISO 15118 plug and charge concept, where the charging process can start without the use of an RFID card. The car itself is identified. On the right top, we have the services that are proposed. We have the enhanced booking service and the routing service, 2 services that aims to enhance the accessibility of the user and reduce the waiting time in front of occupied charging station. The booking service aims to allow users to reserve a charging station, AC or DC charging station in long or short term, depending on the needs of local times. The requirements for the short term and long term reservation are different, and they are considered in the different applications that are provided to the user as mobile application. The routing service aims to provide to the user different routing, dynamic and different routing options to the user, depending on the user preferences, either providing the spot, the end of the trip, or by providing a wider area where the user is interested to drive to. And finally, as regards the services, a smart charging services suite will be developed with serving different business objectives. The first one is to try to create synergies between EV charging demand and local renewable energy resources in order to create a green footprint of the charging process. As regards the DC charging station, to minimize the peak demand impact to the distribution grid that fast charging might provoke, microgrid concept and how electric vehicles can be integrated in a microgrid concept where local renewable energy resources, storage, battery, static storage facilities exist, and how we can minimize the costs as well as the grid impact. And finally, the last service that is developed is the battery predictive diagnostic control, where the battery status and state of health of the battery is monitored in real time while the car is under driving mode. And all these data are stored in a cloud where the battery health is monitored, and we can decide which is the best and the optimal charging profile that should be followed during the charging process in order to minimize the battery degradation and increase the battery life. Finally, on the decision tools for enabling and realizing sustainable deployment of EV charging solutions and services, we have created 2 different tools. The first one is the charging location planning tool, which aims, first of all, to identify the EV charging demand in each area based on the parameters that is used as an input to the tool, and secondly, to identify and suggest which is the optimal technological mix of charging technologies that should be adopted, the number of the charging stations that should be installed, and the locations and areas where these should be deployed. The last one is the incentive scheme and tariff structure proposal, where we have done an extended survey on an overview on the current incentive schemes and tariffs that are adopted by different CPOs and TMSPs in all the 10 demonstrators and pilot site areas. We have identified the differences and how the different strategies as regards the tarification and pricing policies serves the different strategic needs of the local community, which is highly dependent on the e-mobility maturity level. As an outcome of this survey, because there is much diversity, we have created and proposed a generic pricing formula where the different parameters can be modified in order to serve different business objectives and different policies depending on the local needs. For example, if you wish to promote e-mobility, you can have reduced prices, energy prices, or in some cases we have seen that there are zero pricing for the charging in order to promote e-mobility, or you can have dimensions in order to penalize the over-exceeding or the overuse of the charging of the parking slot without charging. So different pricing policies in order to incentivize or penalize the right or the wrong use of the charging network. In this matrix, I will quickly like to show you the different demonstration topics and the different pilot sites, the 10 pilot sites that represent metropolitan areas as well as 10T corridors. So if you're interested in any demonstration topic, you can follow the respective pilot sites in order to see which are the outcomes and the outcomes from the real life experience. And if you're interested in a specific city or a specific area, then you can follow the specific area and the demonstration activities that will be done in the upcoming months. Before closing the presentation, I would like to give you some the main outcomes of the a priori user survey, which was conducted end of 2020. And the main goal of this survey was to track user charging preferences and perception towards the e-mobility. The main reasons for choosing an electric vehicle is the environmental friendliness, which is really important, and this should also be considered not as a transition from internal combustion engines to electric vehicles, but it should also be considered during the charging process, because environmental friendliness was the first reason for selecting an electric vehicle. So we need to ensure the continuity of this green transition, and we should ensure that the charging process and the charging energy is also green. Energy efficiency and lower operational costs are the two main reasons following the environmental friendliness. The selection of the time of the charging depends on different criteria. It might be the charging needs for the next trip. It might be a low threshold that it is placed by the EV user, or the possibility of charging because I have parked in a place where a charging station is available. As regards the flexibility and the realization of smart charging concept, we have seen in home parking as well as in public parking that there is enough time for implementing smart charging concepts. More specifically, as regards the home parking and the home charging, the parking duration was more or less approximately 12 hours, which means that there is a great value and a great time for shifting the charging demand in order to avoid peaks or to create synergies with local renewable energy sources. As regards the public charging, for the slow charging, for the AC, up to 22 kilowatts. The charging duration is approximately less than 3 hours. It deviates between 45 minutes and 3 hours. And for the DC charger, it's about 30 minutes and 1 hour. As regards the sustainability of investment, from the real data from CPOs and TMSPs, we have tracked that the occupancy in our days is quite low. In only essential cases, we have tracked 32% of occupancy in extreme, let's say in very special conditions like in Barcelona city, but more or less the variation is less than 10%, which means that this creates limitations to the profitability of the investment. But in the majority of such cases, we have tracked that the selection of investing in a charging network, in public charging network, even with low occupancy, is selected by CPOs in order to be able to have a market share at the right time. As regards the charging preferences of the user, we have seen that fast charging is the most preferable solution, and this might have to do with, can be explained because the transition from combustion engine and the very fast refueling is also reflected in the charging needs, which means that I need to charge as fast as possible. And the users are willing to pay more for this fast charging option. Finally, most EV drivers were male, and this should be reconsidered and define new strategies in order to involve women in the mobility evolution. I will close my presentation with a project status and which are the next steps. As I told in the start of my presentation, we are in the half of this project, in the second year. We are ending the second year, and we have finalized the design of the solution. These solutions were designed based on the user and system requirement as were tracked from the user survey in order to ensure the user-centric dimension of the solutions, and they are right now validated at laboratory context. From June of this year, next month, we will start the pilot setup, and all the technologies will be traveled to the pilot sites in order to be installed, to be connected with the local system, also the different solutions to be integrated under one pilot context and verify that everything works smoothly. The demonstration activities is planned to start September of this year and will end of 2023. So if you are interested in any demonstration topic or in any technology or service, or if you are interested in general in a more specific area, please follow us in our accounts in Twitter or LinkedIn, or you can be connected to our website in order to check the work progress and the main outcomes of the demonstration activities. Thank you very much for your attention, and once again, I'm really sorry for not being able to be there with you with physical presence.
Okay, thank you very much, Evangelos. We will follow your project and try to keep update on your progress with the demos. So now it's time for our last speaker of this third block. He's Carlos Almeida, CEO and founder of i-HeCoBatt, a company providing a digital platform to support EV charging. And he's presenting also another success story of e-mobility adoption, in this case in Portugal. So Carlos, the floor is yours.
I'm going to share my screen. Hi everyone, I'm Carlos Almeida. I'm the CEO of i-HeCoBatt Electrical Mobility. We started some years ago with the idea of for friends, and we decided to develop a platform, an intelligent and agnostic platform for the electrical vehicle charging ecosystem. And our main focus were the companies, because we looked at the market and the main solutions were not really solving the problems for companies, namely companies that have a huge fleet. So we also developed sustainable charging functionalities integrated with the national grids. And then we evolved for B2B2C solutions and for B2C solutions also. So we now have the full business model here. Our main presence is in Portugal, but we already have projects in Spain and France, and we are expanding to other countries in Europe. We are MSPs, CPOs, and in Portugal we are also electricity suppliers for the electrical mobility. So, as I said, we started by the end of 2018. Well, we started with the concept, then we made the developments. By the end of 2019, we made the incorporation of the company. We applied for several initiatives from the European Commission, namely by the i-HeCoBatt. We were selected for 2 of them. We were very successful, and by the end of 2020, we were invited by i-HeCoBatt for them to be also shareholders of our company. We were also in that year selected as the best Portuguese urban mobility startup of the year. And in April 2021, we launched our commercial services, our SaaS platform, that enable us to provide services to companies to manage their own electrical charging stations and also their EV fleet. We developed several interfaces, one for the infrastructure manager and also for the fleet manager, and another interface for the end users, the people that were really driving the vehicles. In 2021, we also received the Best Mobility Technology Award from the Global Mobile Awards. And this year we were very successful in the fundraising. An investment bank has entered the company and has invested $2.5 million in order to support our expansion in Europe. Last year we also started working on our roadmap. So we are now working on integration of storage with the EV charging, vehicle to home, vehicle to grid, prosumer services, ancillary services, charging with electrical vehicles in terms of autonomous vehicles. And we are also doing some projects with some OEMs regarding advanced fleet management services. So, as I mentioned, we now have solutions for several types of clients. We can address several types of business. And for the B2B2C, we have all of our applications as a white label. So, for example, electrical utility can come to us and use our applications with their own brand. So for B2B, our product, we manage their internal charging stations. We provide several services for them to manage their fleet. We also provide services for allow them to charge anywhere on any network using our mobile app, so with an integrated account. In the future, we will provide the new energy services, and we also provide monetization service. So we have our own network of charging stations, so we allow our private clients, for instance, a private company, okay, so they can share their charging stations. So they are investing in charging stations in order for their electrical fleet to be able to charge inside the company. So during the Saturdays and Sundays, no one is using these infrastructures, these private infrastructures. So we have the platform allows our clients to share and monetize the charging stations in periods where they are not using for themselves. So the public in general can go there and use on that slots of time with a tariff the charging stations. And this is also a way for our clients to have a better return on their investment and a fast payback. And in terms of B2C, we have a mobile app that anyone can download from the store, and you can add your charging station that you have at home. You can charge anywhere, and you can manage all your charging sessions. These are some images of our applications that we have for our clients. Some highlights of some of the functionalities that we have. We allow our customers to interact with the charging. They can decide to start charging when there is a certain level of energy coming from renewable sources. So you can say, I will only start charging when there is 70% of renewable energy being used to produce energy. You can also decide to charge only 5 kilowatts, 5 euros, etc. We provide also several tools for the users to compare charging stations across networks. Sometimes it's difficult for the users to compare the tariffs of different operators, different charging stations. So we have a tool that you can pick different charging stations from different networks, and the tool will compare how much it will cost for you to charge in different charging stations and compare the tariffs for the user to choose the best one. We also have integrated on the app several methods of payment, credit card, and several notifications. A user can ask to be notified when the charging station is free on a street, when it is occupied. We have smart charging. Data analytics is completely agnostic and compatible with several charging stations. We are integrated with several roaming providers, and we are now working on the new energy services. So if anyone has questions, we are available to ask, and we are also interested in participating in future calls and projects. So please contact.
Thank you very much, Carlos. Well, this was the last presentation of the blog. We are really out of time, so we will follow the questions on Slido and come back with answers. And if some of the attendees here have some questions, I think the better is to ask directly to the speakers, taking advantage of the lunchtime. So we are now moving to the last block on circular economy, but before I would like to thank again the speakers. And so I leave you with my colleague Evelina.
Thank you very much, Enrique. And dear participants, it's my pleasure now to invite you all to join our last block of the day and of our Electromobility Technology Workshop, Driving a Greener Value Chain. Firstly, thank you again for remaining with us during these 2 full days and dedicating your attention to ways to improve the whole value chain of EV components. This block will address circular economy topics, aiming to tackle the challenges for dealing with batteries end of life. Raw materials are critical for ensuring the needs of the batteries market, and it seems like one of the winning solutions should be the recycling process. The benefits of this sum up, obviously, to the reduction of waste, especially the toxic waste. Well, even if this block is at the end, and even if this process most of the times is considered as an end process, I believe that we gain more if we will set our mind to start with recycling, and once this solved, we can go to mass production and again to use and improvement. But more solutions and best practices will be provided by the invitees in this last block, and thank you for accepting our invitation, Mr. Javier Lopez Rodriguez from UNE, that will join us online, and I think is already connected. Mr. Justo Garcia, Head of Financing Strategy from Orano, and Dr. Benjamin Wilson, a researcher of Aalto University. And in order for the things to work properly, we need a regulatory and a standardization framework. And I'm inviting Mr. Javier Lopez Rodriguez from UNE to deliver the first presentation. Mr. Lopez is an industrial organization engineer and currently is a standardization project manager within the industry and equipment unit at the standardization department of UNE, giving support and carrying the secretariat of several national and European technical committees in the means of transport sector and participating in several R&I projects related to e-mobility. He has previous experience as a quality manager in metallurgical and automotive industry and as a project manager in building acoustics and R&D projects. Today, the presentation is dedicated to regulatory standardization scenario towards a circular market for EV components. So if the presentation is set and if Mr. Lopez is also online, please, you have the floor. Can you hear us? I think you're muted.
Good morning.
No. Good morning.
Sorry, but just in this moment, my computer was switched off, so I don't know what's happened.
Well,
sorry for the delay.
This hybrid is a challenge for everyone, so please, you can start now.
And thank you very much for the invitation to this workshop and also for all the attendees, and good morning to everybody. I share my screen. Do you see my screen? My presentation?
We see the screen, but not the presentation. We see a black screen, actually.
Oh, sorry. I'll try it again.
Still not. Do you want us to share your presentation?
Wait a moment.
Now we can see the presentation.
Okay.
If you can put it in full screen.
Yes. Now.
Also here. Thank you.
Sorry for these problems, and apologize for not being there with you, but with this new virtual area, we cannot be in two places at the same time, so sorry for this. Well, I try to give you a brief landscape about regulation and the standards that are related to electric vehicles, and especially those that are closer to the circular market. Before starting, let me start with a short introduction about our company. We are UNE, the Spanish Association for Standardization. We are a non-profit, private and independent organization. We are the official standardization body in Spain since 1986. And we develop standards at the national, European, and international level. We have more than 32,000 standards in catalog, and we also have more than 15,000 experts involved in the standardization process, not only at a national level, but also at European and international level. We also integrated the standardization in research and innovation projects. We have been participating in more than 60 projects. And well, in these kind of projects, we provide a first standardization landscape with a list of standards and technical committees that could be related to the project. And also we help the partners in order to develop some standard or something like this as a result of the project. And also we participate in international cooperation projects. Well, as I talk about the standard and regulation, the first point is important to know the difference between them. A standard is a technical document designed to be used as a rule, guideline, or definition. It is based on consolidated results of science, technology, and experience, and it is established by consensus between all the interested parties. And at the end, it is approved by a recognized body. In the case of a national level, in the case of Spain, UNE, at a European level, CEN and CENELEC. What that means is that the standards are developed by the experts. The people that are involved in the development of a standard are the people that have the knowledge, the technical knowledge of some standards. And on the other hand, the European Commissions make policies and regulations. So the main difference between them is that the standard is voluntary, a voluntary document, and the regulation is a mandatory document. So, but sometimes the European Commission asks CEN and CENELEC to develop some standard in order to give response to some essential requirement. It is called a standardization request, and once that these standards are developed, these standards are mandatory because they are cited in some regulation. Okay, regarding the electric vehicle regulation, we have to keep in mind that we are in a scenario with a huge amount of stakeholders, because not only the vehicle manufacturers are involved in the process, but also the components manufacturers. We have to take into account the grid and also the communication. So there are a lot of regulation, but in this case, I try to focus on those regulations that are closer to the electric vehicles and their components. The first one is about the deployment of alternative fuel infrastructure, and it has a supplement with regards to electric buses. And the second one is a directive about batteries and accumulators, and waste batteries and accumulators, that nowadays there are a proposal for regulation to replace this directive. The first one, the directive on the deployment of alternative fuels infrastructure, establish a common framework of measures for the deployment of alternative fuels infrastructure. It also set out a minimum requirements for the building up of alternative fuels infrastructure, including recharging points for electric vehicles, refueling points for natural gas and hydrogen. And it established a common technical specification for such recharging and refueling points and user information requirements. In support of this directive, CEN and CENELEC have developed a guide. This guide is for facilitating the integration of alternative fuels at existing fueling stations and to give guidance to design, authorize, and operate these new multi-fuel stations. And this guide also considers other legislation impacting multi-fuel stations. As I mentioned before, we have to keep in mind that we are in a scenario with several stakeholders. Regarding the directive on batteries and accumulators and waste batteries and accumulators, the current directive establishes rules regarding the placing on the market of batteries and accumulators, and specific rules for the collection, treatment, recycling, and disposal of waste batteries and accumulators. This directive seeks to improve the environmental performance of batteries and accumulators and of the activities of all economic operators involved in the life cycle of batteries and accumulators. And do you see the directive 2006 in the screen?
Now, yes.
Okay, because I think there are some delay. Okay, well, this is the current directive, and the new proposal intends to include requirements on sustainability, safety, labeling, and information, and also the requirement for collection, treatment, recycling of waste batteries, and these regulations shall apply to all batteries. With the new proposal, it is started to talk about terms as reuse and repurposing of rechargeable batteries, but in the current directive, it is not mentioned. Okay. And last but not least, there are standardization requests under the mandate 579, in which the European Commission asked to European standardization bodies to develop standards related to performance, safety, and sustainability requirements for batteries. It is divided in four main topics, and the deadline for the development of standards is December 2025. As you can see, one of these topics is for the reuse and repurposing of rechargeable batteries with internal energy storage. It intends to establish requirements in terms of design, diagnostics and determination of a state of health, and battery evaluation for repairing or repurposing. Currently, in CEN and CENELEC, there are a specific group. They are discussing the work plan to the 25, and they are discussing about the existing standards in order to find some gaps and to analyze the necessity to develop new standards or to review or adapt the standards that are already existing in this case. Well, and what about the standards? In this slide, you can see the map of standardization at the international level, European level, and national level. In all the standardization bodies are involved industry, regulators, and other stakeholders. And the main difference between the national standardization bodies and European and international level is that at international European level, the electrotechnical and telecommunications standards are in a different body, but at the end they are working with the same procedures and these kind of things. Well, and regarding electric vehicles standards, as I mentioned before, we are in a scenario with a lot of stakeholders, so there are a lot of technical committees related to the vehicles and electric vehicles and their components. But I try to focus on the most on the closest committees related to the electric vehicles component. I gathered information about the international level because sometimes, and it is very common in the automotive sector, that the international standardization bodies and the European standardization bodies work jointly, and once that ISO has published their standards, the CEN or CENELEC committees adopt these standards. So in this case, I gathered information of these committees. The first one is the ISO TC 22 Subcommittee 37, electrically propelled vehicles. These work on standards for a specific aspect of electrically propelled road vehicles, the electric propulsion system, related components, and their vehicle integration. This subcommittee is working on safety aspect and technology, performance and energy consumption, rechargeable energy storage, system and components connected to electric propulsion system, requirements for energy transfer, and charging performance. The other subcommittee that are related to electric vehicles are the subcommittee 38, motorcycles and mopeds. This subcommittee is focused on the standardization of motorcycles, mopeds, and their components, but it has a specific working group for electric mopeds and motorcycles. And at IC level, the electrotechnical committees, it exists the TC21 about secondary cells and batteries. This committee works on the standards for secondary cells and batteries related to product safety, testing, and safe application. And the main application of these committees are in the automotive and electrical vehicles. So these committees focus on the specific cells. Sorry, but I think there is a delay. Do you see the information on the...
We can see now motorcycle and mopeds for
yes,
the moment.
Sorry, I think. It's very... I don't know.
It seems like the AI is frozen, so...
Yes. I try to share again my screen.
Please try to share again. Now we can see again the screen, but from the very first slide.
Yes.
Yeah, so we can see the slides changing.
Okay.
And we are now for secondary cells and batteries.
Okay. But I think it goes very slowly, no?
There is a delay between the ones online and what we see in the room, but at some point we will see also the same.
Okay. Well, as I mentioned before, this IEC technical committee is focused on secondary cells and batteries to provide standards for this product related to the product, to safety, testing, safe applications, and these kind of things. And this technical committee is working on the application of the secondary cells batteries in automotive and electrical vehicles. It has more application, but the main application, automotive and electric vehicles. This is the structure. They are working on secondary cells and batteries containing alkaline or other non-acid electrolytes, starting and auxiliary batteries, traction and stationary batteries, safe operation of batteries, secondary high temperature cells and batteries. There are also another technical committee in IEC related to electrical power and energy transfer system for electrically propelled road vehicles. This committee work on standards on electrical power and energy transfer system for electrically propelled road vehicles and industrial trucks. And these standards cover, but are not limited to, general requirements functional requirements, communication between the electric vehicles and the electric vehicles supply equipment, electrical power and energy transfer between electrical vehicle and supply network, and management of the corresponding infrastructures in view of offering the associated value of added service. So these two technical committees are closer to the electrical vehicles component. This is the structure. You can see the topics that they are working on. For example, wireless power transfer, the vehicle charging roaming service, these kind of things. And last but not least, there are a i-HeC subcommittee that is focused on plugs, socket outlets, and couplers for industrial vehicles and for electric vehicles. But it's not the battery of the component, but the connection between the vehicle and the supply network. Well, regarding the standards, we can talk about safety standards for batteries for electric vehicles. At ISO level and i-HeC level, the difference between them is that in ISO level we are talking about the whole system, and at i-HeC level we are talking at a cell system. The ISO 6469 part 1 is the part 1 of a series of standards about electric propelled road vehicles safety specification, but the part 1 is focused on the rechargeable energy storage system. And the i-HeC 62660 part 3 is the part of the secondary ion lithium cells for propulsion of electric road vehicles. The part 3 is about safety requirements. Okay. The ISO 6469 part 1 specifies safety requirements for rechargeable energy storage systems of electrically propelled road vehicles for the protection of persons. It establishes some requirements in terms of mechanical requirements, climatic requirements, simulated vehicle accident requirements, electrical and functional requirements. And it also establishes some requirements for the emission of hazardous gases and other hazardous substances. And well, in some of these requirements, there are specific topics such as thermal shock cycling, vehicle crash, and these specific items. The other standards at cell level is the i-HeC 62660 part 3, and this standard specifies test procedures and acceptance criteria for safety performance of secondary lithium-ion cells and cell blocks used for propulsion of electric vehicles. In this standard, it is established mechanical test, thermal test, and electrical test. We also talk about performance standards for batteries for electric vehicles. We have the ISO 20405 part 4 about test specification for lithium-ion traction battery packs and systems. The part 4 about performance testing, and this document specifies test procedures for the basic characteristics of performance, reliability, and electrical functionality for battery packs and systems for either high power and high energy application. And in the standard that I've mentioned before, the 62660, the part 1 and the part 2, are about performance testing and about reliability and abuse testing. As I mentioned at the previous case, these two standards are focused on the cell, and this is in the whole system. And currently there are two standards about the reuse of secondary batteries. The i-HeC 63330 and the i-HeC 63338. One is for requirements for reuse of secondary batteries, and the second one is general guidance for reuse of secondary cells and batteries. These standards are under development, and it is expected that they are published by the end of the next year, the December 2023. So the main conclusion of this is that usually the standards are required by the market, but sometimes the standards are also required by regulation. In this case, there are a proposal of regulation about batteries and waste batteries, and a mandate on a standardization request in regards on performance, safety, and sustainability requirements for batteries. And also there are 2 standards under development for the reuse of secondary batteries. So that give us an idea that the institutions are worried about the circular economy and this topic, and they include this topic, the circular markets, in their documents and in their policies. So that's all from my side. Sorry for the connection problems and for the delay of the presentation.
Thank you very much for the presentation. And for the extensive overview of regulations and standards on batteries. With so little regulation on recycling, the main motivation for battery recycling remains the recovery of critical raw materials. And for this, we have Mr. Justo Garcia, Head of Financing Strategy at Orano, to present a perspective on the industrial strategy for battery recycling. Justo has more than 20 years of professional experience in Orano, with various positions from engineering manager to R&D program manager. In 2019, Justo launched a project dedicated to the development of innovative battery recycling and the setup of a joint research laboratory in Grenoble. In December 21, Justo was elected as a member of the executive board of BEPA. Today is about innovative battery recycling solutions.
Okay, so thank you very much for the introduction, and so I'm very glad to attend this workshop and to share with you the battery recycling solution that has been developed by Orano. Okay, so I will. So here it's the agenda of the presentation. So some word about the context. So we'll present the disruptive process for the battery recycling that has been developed, and also our industrial strategy for the electric vehicle battery recycling. And so some word about to conclude the presentation. Okay, so the context. I expect that so you are aware of that there are strong growth in Europe and in terms of battery production capacity. And so today we have about it's expected to have more than 500 gigawatt by the end of 2028, and more than 1,000 gigawatt will be expected to be later. So this big amount, okay. And here it's also the figure that's the installed battery production capacity in Europe could reach that more than 1,000 gigawatt. Okay, and so here, so this map illustrates that all the Europe is planning to install and develop the battery capacities. But also, we need also to have in mind that after the use of the battery, we have to prepare so the end of life of the battery and so to recycle. And even in parallel with the installation and the erection of the gigafactory, some players are positioning themselves to be also recycling in Europe. the lithium-ion battery recycling market is driven by the growing economic interest of the activity and increasingly favorable international regulation. So we have the growing of the demand for the lithium batteries. Also the growth is the price of the metals that prove the interest to reuse the materials that are in the end-of-life batteries. And so the international regulation is favorable to reuse the material. And so, as I explained previously by the Spanish regulator, that Europe prepare the new regulation dedicated to the batteries, and the one key element will be so the obligation to reuse some part of the metal in the new production. And so it's very important, and it's favorable for the industry of the recycling. And so here I sum up the main challenge for the industrial of the electrical vehicle. So one of the main challenges is to reduce the CO2 emission through the entire life cycle of the battery, and the recycling will be also an important part. Also, it's important to find a sustainable solution for the end of life of batteries. Also create a closed material loop that are adaptable for the future electrical battery developments. Also increase the amount of strategic material recycled for the EV batteries. And also to integrate a European solution in order to support the local jobs, the growth, and the competitiveness. So all these elements are very important, and we expect that Orano could contribute to the challenge, to solve this challenge. Okay, so some word about the disruptive process. I will start with a very short presentation of Orano. Orano activities are currently focused on the nuclear energy. And so that it could be strange that we are here to propose a new solution to the recycling. But so Orano is striving to expand in low carbon economy and the recycling of strategic material for the energy transition. It makes sense because from the beginning, Orano here in the circular economy, because Orano is involved in the mining to extract the uranium, but also to transform the uranium to conversion, enrich the uranium, and also it's involved in the recycling. So Orano recycle all the nuclear fuel in France, but also some fuel from Europe. And so with this recycling, so we retrieve uranium and plutonium, and we could manufacture new assemblies that are currently in operation in reactors. So we close the loop in nuclear. Based on the competencies that Orano has in mining, but also in conversion arrangement, also in the recycling, the decommissioning, also the engineering, Orano has the competencies to develop and to provide and to propose a new solution for the recycling of the batteries. So, but Orano has decided also to launch a strategic partnership with the CA and the branch, the Lytton, that is devoted to the new energy and the recycling. So we join the expertise from Orano with the expertise of CA in order to propose a disruptive process for the battery recycling. No pyrometallurgy in the whole process. That process could be applied to all type of chemistry and type of modules. The objective is to have a high purity of recycled material that could be reusable for the EV battery cycle, And all this process include innovation and patents. Orano decided to to invest in this new activity but would like to propose a disruptive solution, because the current solution, mainly 90% of the recycling of the battery, it's based on pyrometallurgy, and so we consider it's not the best solution, and so we want to propose something very disruptive, and in order to propose something interesting for the industry. Okay, so some word about the process. So Orano should be integrated in the closed loop of the lithium-ion battery by developing an efficient and cost-effective recycling process. So it's a classical presentation of the recycling. So we start from the dismantling. So we need to collect the batteries and to dismantle the battery, because a battery, it's around 300 or 400 kilograms of metals, and inside there are some modules. So we need to dismantle and to retrieve the module, and the second step of the process is the desactivation at the module level. So the self-desactivation is the key of the process. It's very disruptive, so we deactivate it in an inert environment. I could not disclose information about that, but after this operation, we could access safely of all the elements that is part of the batteries, of the modules. And the advantage of our process is that we don't modify the different elements. There are no chemical transformation, no degradation of the different materials. And that's the advantage of that. We could valorize better all the different elements. After, we can have some operation to separate the to cut and to crush the element in order to access at the optimized size in order to continue the process, that in order to separate the different elements. And so we have the first element that we could separate is the graphite. That is very interesting thing, that it's a very differentiator to the other process, because in the other process we lost the graphite, or we have the graphite during some part of the graphite, you have to manage it at the hydrometallurgical step. So we separate the graphite. After, we can retrieve the electrolyte. We can separate the different plastic, steel, or casing of the module. And so we have at the end not a black mass, that it's a common word that it's used for the competitor process. We have a clean active mass, and so this element it's mainly composed of the main elements that we want to valorize: the cobalt, the nickel, lithium, and manganese. And this active mass will be processed in the at the step metal separation. It's the hydrometallurgical process. And so we use classical extraction system, solvent extraction system, and so on. So we retrieve the metal salts, cobalt, nickel, lithium, and manganese. With this, one of the advantages of our process that as we have retrieved the main part of the graphite, we process we process less material in the hydrometallurgical step, that reduce the cost of the treatment. with these metals, the salts, we could synthesize precursors and in order to manufacture after the cathode active material. So mainly Orano, it's okay. So yes, yeah. Okay, it's a presentation of the process, of the pre-treatment process and the hydrometallurgical process. It's exactly what I explained you previously. Here it's only to indicate what are the key parameter indicator of our project, of our process. So we indicate the strategic research agenda parameters that are being defined by the European Commission, and so our objective, and so that we achieve at the micropilot level, and the pilot, I'll explain that. So we achieve totally the efficiency and more, because we could retrieve, as I explained, the graphite, the electrolyte, the manganese, the aluminium, and the plastics that are not covered by not the regulation, but what it's currently indicate in the SARA targets. Yes. Oh. Sorry. No, it's okay. It's okay. 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 So currently, so we have a French consortium that's working on this new process. So we have involved in this project PAPREC, that is devoted to the part of the dismantling of the batteries. MTB, that it's a supplier of some equipment for the secondary sorting. CEA-Liten, that it's our main partner in the R&D activities. And SAFT, that will reuse, that will manufacture new cells using materials that have been processed in our entire process. And so we are currently there are under construction two pilot plants, one dedicated to the pre-treatment and the second plant is dedicated to the hydrometallurgical plant. These two pilots are located in our premise at Orano site in Bessines-sur-Gartempe, in the center of France. Okay, here I want to underline that our project is supported by at national level and regional level in France. So we receive some subsidies from the Nouvelle-Aquitaine region and the French government within the framework of the French Recovery Plan. And so we are under negotiation for the two grants from Horizon Europe program. So we expect that we'll start. One project has been started, but officially we have not signed, so that's why I could not disclose some information. And the second one will be will be signed also in the next days or weeks, and we expect that it will start in the next months. Okay, so what is the strategy of Orano? So Orano is on the track to enter in the electrical vehicle battery recycling sector by 2025. So we start from, as you see at this moment. So we are manufacturing two pilot plants, and that plant will be operated in the next weeks and months. So we expect at the end they could operate, and so we could pilot in order to validate the performance of our system, of our process, and we expect to start the construction of the new operation plant, the two operation plants, one dedicated for the pretreatment and the second one for the recycling next year, in order to start the construction in 2044, and the operation could be started in 2025. What is also interesting to explain that as our system could be separated in two phases, the pretreatment and the recycling, the hydrometallurgical process. We have in mind to have a decentralized implementation of the pretreatment in order to have several pretreatment units that will be feed one hydrometallurgical plant. And the advantage of this decentralized implementation that will reduce the transport cost between the pretreatment and the collect center to the hydrometallurgical plant. That would be interesting. Yes. So conclusion. So Orano developed a new, safe and disruptive hydrometallurgical recycling process. So we reduce the CO2 compared to the pyrometallurgical recycling. We have a safe pretreatment step that deactivate fully the EV batteries. The process is applicable for all type of batteries, type and chemistries, and so we could have high priority output that allow to close to allow a closed loop solution in the battery cycle, compliant with the forthcoming European regulation. And so we have an industrial project developed at the European scale, and so the process fully operational by 2025. That includes decentralized pretreatment facility allowing deactivation, dismantling, and material concentration, further reducing environmental impact and cost by simplifying transportation to a central hydrometallurgical plant. And that's all for me. Thanks.
Thank you very much for the industrial perspective and also for the promising next steps. We look forward for the results or for the evolution of these new projects and activities. And we will go for the next presentation, where Dr. Benjamin Wilson will introduce us a best practice example of a circular economy ecosystem of lithium-ion batteries, metals. And Dr. Benjamin Wilson is currently the staff scientist of raw materials, metallurgy and electrochemistry at the School of Chemical Engineering of Aalto University in Finland. He has over 20 years of experience from across Europe in materials, sustainability and circular economy of metals, with an emphasis on battery recycling methodologies. Today, he will introduce the BAT Circle 2.0 project and the Finland-based circular ecosystem of battery metals. And we have also some information materials in the back of the room. So please, if you are interested, you can grab one on the way out. Thank you. You have the floor.
So, good afternoon, everyone. Thank you for the kind introduction and the kind invitation to come here and meet you all in person. It's been a while for a lot of us, I know. So it's good to see so many faces are still here, and the last one that's holding you up before lunch, so I'll try and keep this short and sweet. So as was introduced, I'll be talking today about BAT Circle 2.0. It's a Finland-based ecosystem of battery metals. So what does that mean? Well, why Finland? Well, as you can see here from what's on the screen, in fact, Finland is well blessed with all the aspects related to battery materials and batteries. Has one of the largest lithium deposits within the European Union. It's also rich in primary raw materials, that we not just the obvious ones, where we're thinking lithium, cobalt, nickel, but we also have copper, silver, gold, and a lot of other mineral wealth as well. In fact, we also have some significant natural graphite deposits which have recently been identified, and steps have been taken to exploit this, such that Europe can have a source of graphite which is sustainable and comes from a good source. It's interestingly, in fact, as well, that despite our small size, 10% of all global cobalt is refined in Finland, and about 4% of nickel is also refined there. So it is, quite a major player when it comes to the metals. We have the industrial players, Nornickel, Fribourg Cobalt, Boliden, so you name it. These are all essential parts of the value chain related to batteries. We also have world-class minerals processing and metallurgical know-how. Many of you have maybe heard of Outokumpu, Autotech Technologies. They're very much based in this. And Finland as a whole has a low carbon dioxide electricity production. 80% of it comes from nuclear, wind, solar, hydro. So thankfully, when Mr. Putin turned off the electricity from Russia, it didn't affect us too much. So what is the BAT Circle 2.0? Well, it's a consortium. It's a joint industry academia project. It's running this time from 21 to 24, so we're just kind of getting into the second phase here. It's coordinated by ourselves at Aalto University, but it does involve other research partners. So we have GTK, that is the Geological Survey of Finland. We have the University of Oulu, VTT, it's the Research Centre of Finland, so it's dedicated to taking things from the lab scale to more industrial. Lappeenranta University, University of Eastern Finland. So these are the people who form the core of the academic staff, but it's also, it involves industry, and you can see here there's, how should I say, a lot of 15 companies involved here that cover the whole spectrum. So we have the Akusa, who are looking at the crushing and creation of the black mass. We have Graphene Tech, so looking at how should I say, how do we get the raw materials, along with Finnish Metals Group and Terrafemma. Then we have like the users, Broadbit, Fortum, Calibre also there is making lithium. And we're trying to cover the whole thing from raw materials through the formation of precursor materials into the batteries, into the use, and then the part that I'm most interested in myself is the recycling. Within this, we have open research, and we also have confidential R&D research between the different companies. So the idea behind the BAT Circle in its first iteration was to try and create this ecosystem to get companies from different parts of the value chain talking to each other, because they have a lot in common. Even if they're not so related directly, they're still part of the same chain. So what are our goals? Well, they're quite straightforward. Improving the manufacturing process of the mining industry. Can we make the mining more sustainable? Can we make it more, get a better return on our minerals? Can we get as much of the valuable materials out and reduce the waste? Also helping boost the metals and battery chemicals industries in Finland. Increase the recycling of lithium-ion batteries. So we heard quite a lot from Justo related to that. But also, as I say, strengthen this cooperation between research and industry, as trying to cross this valley or desert where we do the research and then it takes a long time or never actually gets into practical application. So by getting everyone around, all the stakeholders together in the same place, we can try and get these things working from the start and not coming from the lab with a beaker-sized thing and saying, can we do this on an industrial scale? No, let's get the people in from the start. We also have an advisory board, so it's part of an extended network which is within Finland but also multinational, and they advise us or can take information from our BAT Circle related to their interests. So I'll talk a little bit about the open research, how it is. I mean, we follow the circle of the circular economy as it relates to batteries, but here we just put them in a linear form so it's easier to see. So we have different work packages. First one is about batteries, minerals exploitation, and responsible mining. We've been having sort of discussions over lunch and over coffee and things. Europe has resources, but many countries will not promote mining. Yeah? So one way to do that in Finland, actually Finland's quite pro-mining, but it takes 10, 15 years to open a new mine and get it in production. So part of that is to take our partners who are involved in mining and try to demonstrate, along with the geologists, how we're doing the minerals exploitation, how we can do it in a responsible, reassure people, reassure citizens that it can be done with the least impact on the environment. Enhancing the battery recycling, so we're looking at both how recycling is done now, taking black mass, but also looking at future battery chemistries, which we're also involved in creating, and how can we have the recycling process already in place before the batteries actually come to the end of life in 15, 20 years' time. So part of that is looking at advanced minerals and metals processing. How can we create the materials that are going to be used in the new state-of-the-art battery materials? And finally, we're looking at circular battery value systems. So what are the business things behind this? We can't do these things in isolation. You can have the best recycling system you want, but if it's not economic, people are not going to adopt it. So how do we look at those things? Of course, we always have a work package dedicated to project management, but also because we have been highlighted by the European Union as a good example of ecosystems which could be rolled out across Europe on a regional basis or a national basis, or even further than that. We are heavily involved in Batteries Europe, leading the discussions, feeding our information and giving feedback. So just to give you a couple of examples of the things we're involved in. So we have enhanced battery recycling, that's kind of key, and it's really very similar to what Justo was talking about. But we're just looking at what you get now, industrial black mass. You can try and sieve it and shake it and things like that and try and separate out the bits you want. Enrich the cobalt or the nickel parts, try and get rid of the plastics and things like that. One of the key problems that we have is, we have the electrode materials, you have aluminium, you have copper, you can have the casings and things like that. So what's currently done in a lot of places is that you do hydrometallurgical processing, so you leach with something like sulfuric acid, this is good, but it's relatively slow. So you can enhance that by adding like an oxidizing agent, something like hydrogen peroxide. This is quite typical to be used, and it's one of the most common and, more environmentally friendly oxidants that you can use. Fortunately, when you do this separation of battery materials, mostly you'll still have copper in there, you'll have aluminium in there, and you'll also have iron in there from the battery casings. So by putting peroxide in there, all these three metals actually react with the peroxide and reduce its oxidating power. So one thing that we've looked at is actually exploiting those metals. They can be used as a sort of oxidating reduction system within the leaching itself. So you don't need the peroxide to start with. You can carry out the leaching using the metals in there that you don't want, so you can exploit those. And then if needs be, you can add peroxide in a second step and then finish the leaching process. Why does this have an advantage? Well, you don't have to spend too much trying to separate out the materials as much as possible. It will tolerate a certain window of these copper and iron and things like that. And also you end up using less peroxide, which itself has quite a huge environmental footprint when you look at its LCA. Other things that we're looking at is actually the minerals and metals processing. So of course we're looking at the flotation, looking at different properties of, things that will help the flotation, so surfactants and things like that. So we're looking at biological-based surfactants, which are much greener. But the case that you can see here on the screen is that you can take battery waste, the black mass, and you can actually take slag from metal processing, which is also a waste product, which needs to be dealt with. And by mixing those together and carrying out some flotation on grinding and various steps, you can actually get the metals out of the slag and out of the battery waste. So you're killing two birds with one stone. And then that can be just copper slag. It can also be slag from nickel processing. So, you are taking two wastes, mixing them together and reducing their environmental impact in terms of their metal content, which can sometimes be an issue, and also getting materials that can be fed back into the battery chain. When we're thinking about state-of-the-art battery materials processing, we have a lot of colleagues looking at brand new chemistries, low cobalt, cobalt-free, things like that. They've also, some of my colleagues have come up with a system where they can actually remove the electrodes from batteries, relithiate them and put them back again. So you don't even have to go through the whole manufacturing process. You just, treat the electrodes and place them back in the batteries themselves. But one aspect that many people don't realize with battery materials processing, it produces a lot of sodium sulfate as a byproduct. And you say to yourself, oh, sodium sulfate, I've used it in the lab, we probably have some in the kitchen. It's not too dangerous for the environment. The fact is, when you've got thousands and thousands of litres of it, it is a problem. You can't just dump it in the sea. You can't just, especially in the Baltic, it would cause too many issues, too much over-salinization, and it's not good for the environment. So, because we have this network of companies, we found that this byproduct can actually be fed to the steel industry and used to pickle steel to remove the oxide layer after production. So we're taking the waste from battery material process, giving it to the steel industry, and actually, as you can see here, using the electrochemical pickling process that they typically do with hydrochloric acid, in most cases, you can actually remove the oxide layer really well as well. So once again, we're taking a waste, which otherwise would have to be dealt with very expensively. It can be sold to the steel industry and used, so promoting circular economy and more sustainable outcomes. One of the other things that we've been looking at is taking statistical entropy analysis and applying that to the resources within the circular economy related to batteries. So what do we mean by this is, well, this has been, system has been very much used in resource management for a number of years, but it's very rarely applied in the circular economy as yet. So the idea being is that as you're moving from the metal through the circular economy or through the circular process, you're becoming more and more dilute. So what you need to do is then, okay, how do I then, in the case of batteries, once I've crushed them, how can I get it back to a more enriched material that I want to look at? You can statistically, entropically analyze this such that you can say, okay, if I sieve at this level or I crush at this level, it will produce a more rich system than it would if I did it in another way. So it's actually looking at, how to say, producing the best resources from a statistical entropical state, and also taking into consideration that everything will go to entropy in the end. So at what point is there too much energy required to take the materials out that then you have to just say it's almost waste or needs an alternative use. So there's a lot of publications. I won't go into them today. They're just there for reference for you in the past, in the future, sorry. So we have Batteries Europe. So we are in BAT Circle involved in work group 2, which is raw materials and recycling. As you can see, there's 6 work groups. So new emerging battery technologies, advanced materials, manufacturing cell design, application integration module, application of integration and stationary batteries. So, we in Finland are really driving and have been asked by the European Union to drive the Batteries Europe in terms of raw materials and recycling. Part of that, we do these regular roadmaps. The links are here for you. And it's very interesting because what we do in Batteries Europe as a whole, and in particular raw materials and recycling, this is what influences the European Union to decide on Horizon Europe calls. So these are if you're in the making proposals or looking for where the future will be lying, these are worth reading, because normally within the next 2 years or so, these will be on the roadmap and actually in the Horizon 2020 calls. So, because this is the last presentation and thinking about the discussions that are going to carry on after this in the afternoon for those of you who are going to be there. So, through our work in BAT Circle, we've identified some research and innovation priorities which are listed here. A lot of them have been highlighted by other presenters through the course of this 2 days, but it's worth writing them down here so you can have them as a ready reference. So we need to harmonise the raw material resources. There's no standard method at the minute different geology surveys do it in different ways. So actually Europe, we know we have an issue with critical raw materials. Well, in fact, all materials are critical when you start thinking about it. But we need a better estimation of what we actually have so we can approach the problem. Also, how can we trace these materials once they're in the value chain? You know? Okay, the cobalt originally came from Congo. Now it's been recycled a number of times. Does it still have that identity, or is it being greenwashed because it's been recycled? You know, energy recovery, Justo was talking about it. You know, a lot of batteries are still not completely discharged. So why waste that energy? Can we capture it to do something, even if it's just a heat, or do some small powering in the factories where it's been recycled? We need to think about state of health, state of charge of batteries. We need to have a standardized network for that, because at end of life, if it's not the same, people will be trying to compare different things, and it won't make sense. It'll confuse the consumer. It'll confuse even the people in the industry. If we're talking, if we think about imperial units versus metric, people get confused and accidents do happen. So it's best to try and get a standard now while we're talking about it. Of course, we have to improve the recycling processes, but we also have to say, okay, what targets are realistic? Is it weight of battery? Is it amount of material, amount of certain elements, that kind of thing? The big thing as well, of course, is electrification doesn't just mean driving a car, it also means industry. Can we electrify it and reduce its carbon footprint? It's no good having a recycling process that is really good if the carbon footprint of it is so massive that it offsets the life of the battery itself. Also, we need to think of better ways to valorize anode materials from end-of-life batteries. And if we're going a bit beyond that, thinking about the environmental impacts, then we need more data. Life cycle analysis, life cycle inventories, there's some, but we always need more. If you try and do it now, a lot of the data there is not specific for the battery industry or primary and secondary materials or battery chemicals. So we need to be open about the things we're doing and give that data as a sort of first step towards harmonizing and getting a better handle on our environmental footprints. We also have to take the social aspects into consideration. How damaging for the mine is for the environment is one thing, but how about the social impacts of having it? How about the social impacts on people's jobs when we start thinking about replacing the automotive industry? So these things also have social things. Forecasting of LCA, standards for the sourcing of materials, as I said, whether it's outside or within the EU. And the big thing that's talked about as well, of course, is the battery passport. Can we take this data from the mine all the way through its life, back to recycling, second life, so everyone can make a judged decision exactly what the battery means, and can it be used for the grid, or does it already have to be recycled? So I can't do this on my own, of course. So here's some of my colleagues. So Mari Lundström in the center, she is the lead on the BAT Circle as the project leader, but also in the EU BAT Circle, so liaising with Horizon Europe and Batteries Europe. We have 2 project managers. But in Alta, we have 6 professors in charge of the parts that we take into consideration. So hydrometallurgy, minerals processing, thermodynamics and modeling, metallurgy, pyrometallurgy as well, electrochemical engine conversion, but also engineering and geology. So as we say, within our groups, we have the full spectrum of the value chain related to the batteries. So thank you for your attention. If you have any questions, I will be at lunch, so please feel free to disturb me over a sandwich, and thank you all for being here.
Thank you, Benjamin, for the presentation, and I remind you that you can take one material that presents a BAT Circle 2.0 project, and they were brought all the way from Finland, so take the opportunity.
Please take them. I have to take them back.
Yes, the carbon footprint will influence a bit. And I would like to thank all the speakers, Javier López Rodriguez in online, Justo Garcia and Benjamin Wilson here with us. Unfortunately, the time is not a friend of ours now, so we will not take any questions, but Slido will remain open during the day. So if you have specific questions, you can put them there. We will follow them forward to the speakers. And this is an opportunity for you to follow our event page, where you will find the answers to these questions. Also, the ones that are here, of course, as Benjamin already said, can take advantage of the lunch and of sharing ideas and clarifying any doubts if needed. Now we have come to the end of our second day of Innovation and Networking Days on battery technologies and electric vehicles towards a greener value chain. And I will invite Evelina Castellana, EU project coordinator at LOMARTOV, to sum up the talks these 2 days. Hard mission. And afterwards, we will enjoy the lunch, of course, on the terrace, as we are used, and we wish bon appetit for the ones at home. We will be back afterwards at 3:15 with the ones in person registered for the Spertus seminar. So, Evelina, you have the floor.
Thank you, Michaela. So, as you announced, we've now reached the end of the Electromobility Technology Workshop, Driving a Greener Value Chain by i-HeCoBatt. So I would like to thank you all on behalf of the project i-HeCoBatt Consortium and all from all LOMARTOV team and our 35 speakers and all the attendees who assisted us during 1.5 days exchanging knowledge and inspiration about this highly interesting topic. I think these have been very fruitful days. So thanks also to our panelists reflecting the excellence of the European research panorama. We have thoroughly explored the whole value chain of the electric vehicle and its components, given an overview of the challenges, but also the latest innovations in the research and innovation field is providing and implemented when it comes to different aspects. So first of all, the provision of efficient, safe, abundant, and sustainable materials for the next generation batteries. Secondly, the latest research trends in electric vehicle components and also in the infrastructure needed to boost their massification and allowing the implementation of real cases such those seen in different projects that were here with us during these 2 days. And lastly, the most important aspect to ensure the real feasibility of the electric vehicle market, the circularity and the most promising recycling strategy of the raw materials and the main components of electric vehicles. We hope you have enjoyed this presentation and that you will bring this knowledge and ideas to your respective field in order to contribute to the establishment of zero-emission future of our road mobility. So I thank you all once again. We invite you to join us for lunch on the terrace, and we thank all our attendees in YouTube. Unfortunately, the streaming will end up here. So yes, we wish a good rest of the day to our attendees on YouTube. And for those of you who are staying in Spertus, we are meeting at 3:15. Thank you. Thank you very much and enjoy the rest of the day.